Let's talk about mathematics and understand why it is important for every engineer. Mathematics is the base of engineering. It is a fundamental requirement that everyone must master. Right from discrete mathematics, number theory, set theory, graphs, these are the basic things that every CS engineer must master. It is not just important for clearing interviews, but it is also vital for growth within a company itself. Facebook, Google, and the likes ask numerous questions that are based on maths. GCD, prime numbers, modular arithmetics are common areas on which you would be often tested during your interviews. So prepare your mathematics well.
Hey folks, I welcome you all to Scalar Academy's YouTube channel. So if you want to be a good programmer, then you need to have a good mathematical aptitude. Or in other words, you need to have mathematical way of thinking to solve the coding problems which you face. So understanding the importance of this, we have brought you this tutorial on mathematics for programming. Now, before we start off, I'd like to request you guys to subscribe to our channel and also hit the bell icon so that you do not miss out on our upcoming videos. So on that note, let's get started.
Hello, so we are back with a live class. Today's topic is factorization. These classes are for people who want to become better programmers, right? Better at DSN algorithms. So please make sure that you subscribe to the channel and press the bell icon to get notifications, right, about any new videos. As always, there will also be a practice set available to you. This practice set will have a few problems so that you can apply whatever you learn in today's class, right? Actually practicing the problems will help solidify the concepts. All right. So we are going to cover factorization today. Now, factorization is a topic of mathematics. All right. And as computer programmers, you will need to have a decent understanding of mathematics. In fact, I mean, in all sciences, and computer science is a science, right? The stronger you are at maths, the easier your life will be. Now, programmers, you don't have to be very good at mathematics, but there are certain areas that you need to focus on to be a good programmer. Now, these topics are like discrete math, probability, statistics, combinatorics, linear algebra, modular arithmetic, number theory, graph theory, right? So it is still a very large section of topics that you will need to be a very good programmer. So we're going to start with that. And today's topic is from number theory, and the topic is factorization. All right. So let us begin. All right. Cool. So before we begin, let us start with a question directly, right? Let us say that you have been given a number n, all right? And this is an integer. This is an integer. In fact, this is a positive integer, right? Your task is to find all the factors of this number, right? So for example, let us suppose that you have a number like 16, perhaps. Right, so can someone tell me all the factors of 60? What all numbers is 60 divisible by? So when we're talking about factors, we are talking about the positive numbers, right? The positive integers that divide 60, right? And do not leave a remainder. So what numbers are those? So firstly, we have 1, right? Then does 2 divide 60? Yes, it does. So we have 2. Similarly, 3 divides 60. 4 also divides 60. 5 does, 6 does, 7 does not really divide 60, right? Now 8 also does not divide 60, neither does 9, 10 does, right? 10 definitely divides 60. After that, what numbers we have? So we have 12, right? Then we have 15, then we have 20, right? What more? We have 30 and 60, right? So these are all the different factors of 60. Right? Cool. Now, before we dive further into this problem, let us try to draw some observations. Right? Let us try to draw some observations and see if there is some pattern to what the factors of a particular number are, right? So first of all, you will notice that 1 and the number itself, they are always factors of this number. Yes, do you agree? Well, 1 divides every single number, and if you have a number, let us say n, then that number will divide itself, right? So that has to be a factor. What else do we notice over here? Is there any other pattern that we notice over here? Yes? So we notice one more thing. So the first thing is that 1 and n are divisors of n. The second thing that we notice is that factors come in pairs. Factors come in pairs. What do I mean by that? I mean that given any factor, there is a corresponding factor. Right? So if I pair 1 with 60, then I will get 60, right? 1 times 60 equals to 60. Similarly, if I pair 2 with 30, then I once again get 60. So 2 times 30 is 60. Similarly, 3 times 20 is 60. 4 times 15 is 60. 5 times 12 is 60. 6 times 10 is 60, right? And then if I continue from here on, you will see that I will just repeat these things, right? So I will just repeat these things. I will say 10 times 6 is 60, right? So 10 and 6 have been repeated. Similarly, I will next say 12 times 5 is 60. So after all this, the numbers are being repeated. Is that clear? The factors will always come in pairs, right? That is the main observation that we draw from. All right. Now, given that we have these observations, could we write a program? Could we write a function, let us say find factors, right? That takes an integer n, and let's suppose prints out all the factors of n. So let us in fact call this, instead of find n, let us call this print factors. This function accepts an n, and it is supposed to print out all the different factors of n. Right. So what approach do we see over here? So one way to do this would be the naive way, right? The very, very simple way. The first way would be to go through all the numbers. Go through all the possible divisors. Right? So to go through all the possible divisors, we will need a few more observations, right? Let us quickly see what those observations are. So the first observation was that 1 and n are divisors of n. There is one hidden observation over here. Right? Let me mark this as the third observation. And that observation is there are no divisors that are less than 1, and there are no divisors that are greater than n. Right? So the divisors, so 1 is the smallest divisor and n is the largest divisor. Yes? Does that make sense? So when I am trying to find the divisors of a particular number, I only have to go from 1 all the way till n. Right? Because I cannot have divisors that are greater than n. Does that make sense? Is that part clear? Right? Perfect. So how do we write this program then? This is a very simple for loop. So we will say for I goes from 1, right, all the way till n, and we'll increment I. So we'll go through all the different numbers. What we will do inside this? We will check if n mod I equals to 0. Right? So everyone is familiar with this mod operation, right? This is the remainder operation. This says that when we divide n by I, then what is the remainder? Is that remainder 0? If that remainder is 0, then I must be a factor, right? I must be a factor. Then what do? We simply print I, right? So this is our code for factorization, right? Cool. Now this is the first approach. This is very naive. We can do much better than this. But why is this naive? So let us analyze the time complexity of this particular program. So how much time does this take? If I have a number n, then what is the time complexity of this particular program? Well, this is a simple for loop, right? We are going from 1 all the way till n. So this is linear. In fact, this takes order of n time, right? Cool. Can we do better? Well, certainly we can. Certainly we can. So the first thing that you will notice over here is that whenever you're looking at these numbers, we know that the largest factor is the number itself. Right? The largest factor is the number itself. But what is the second largest factor? How big can the second largest factor be? So I know that the largest factor is n itself. Right? What about the second largest factor? Second largest, that must be less than or equal to n by 2. Right? That factor must be less than or equal to n by 2. Why? Because if it is greater than n by 2, then its corresponding pair, right? Divisors always come in pair. Right? Factors always come in pair. Its corresponding pair will not be an integer. Right? 2 is the smallest integer that might divide this number apart from 1. Right? So we know that the second largest has to be less than or equal to n by 2. So one thing that we can do over here right away is, instead of having this loop from 1 till n, right? Instead of having this loop from 1 till n, we can modify this. Right? We can modify this. So let me just modify this over here. I will say I is less than or equal to n by 2. Right? And notice that this is integer division over here. Integer division. Right? So in this loop, I will print all these divisors, but now I do not print n, right? I have missed n now. So I will have to add another statement over here, which will simply say print n. Is that clear? Because now our loop is going from 1 all the way to n by 2. So I will not print out n in this loop. I'll have to print it separately. Yes? So how much time did we save just now? We made a program twice as fast. Right? That's very nice, right? We certainly made a program twice as fast. Asymptotically, it is still linear. Right? It is still order of n time, but practically it is twice as fast. Right? Perfect. All right. So can we extend this observation further? What about the third largest factor? What about the third largest factor? How large can that be? Well, if the number is divisible by 3, then the third largest factor can be up till n by 3, right? Does that make sense? So third largest factor has to be at max. It has to be less than or equal to n by 3. Similarly, the fourth largest factor has to be less than or equal to n by 4, right? And so on. So we see this pattern over here. Is that clear? Cool. Now the question is, we could use this particular observation to reduce our time complexity by half. How do we utilize all these observations? How do we really utilize all these observations? So to do this, let us make one more observation. Right? Let us actually go back to this observation that we had previously. Let us look at this thing once again. Okay. So let us say that instead of going from 1 all the way till 60, right? Instead of going from 1 all the way till 60, we only go till this midway point. Right? You clearly see that there is this midway point over here. After this midway point, so this is the midpoint. After this midpoint, the numbers will repeat. Yes, 6 into 10 repeats as 10 into 6. 5 into 12 will be repeated as 12 into 5, and so on. Right? So we only need to go till this particular point. We only need to consider this half. We do not need to consider the other half. All right. So if we are considering this half, then we have to go from 1 all the way till what number? We have to go from 1 all the way till this number. How do we find what this number is? How do we find what this number is? So basically, we are looking for a number I, right? We are looking for a number I such that I times something else. First of all, this should be equal to n, right? Because they are numbers, they are factors, right? So I times something should be equal to n. Secondly, I am looking for a number such that I is less than or equal to this something, right? Because so basically, I'm going till 6 because the pair of 6 or the number which is paired with 6 is greater than 6, right? 10 is greater than 6. If I go any higher, then the numbers will swap. 10 will now become, the first number will become greater than 6 now. Right? So we are looking for a number over here that follows this property. Okay, so if this is x, then what can I say from here? I can say that x equals to n divided by I. Right, so I can put the value of x over here. I will get I is less than equal to n divided by I. What can I get from this? I can move this I to the left hand side. Right, so I will get I squared is less than or equal to n. And what does this tell me? This tells me that these numbers, they must be less than or equal to. So I must be less than or equal to square root of n. Is this part clear? Is this derivation clear? This is very simple. A lot of you might already know this, but it is important from where this is derived. Right? This square root sign, this is not magic. All right. So once again, we are saying that we are looking for a number I, we are looking for a factor I, such that its paired factor, when we multiply them, we get n. Right? They are factors. Now we are also saying that, okay, we are going to make sure that this factor must be less than equal to its pair. Right? This factor must be less than equal to its pair, because if it is greater than its pair, then we are just repeating ourselves. Right? Because 2 times 3 is the same as 3 times 2. So we only need to make sure that this number is smaller than this number. Otherwise, we will be repeating ourselves. So we put this in the equation. We say I is less than equal to n by I, which means that I square is less than equal to n, which means that I is less than equal to square root of n. So what did we get from here? So now we can improve our program. We can now say that we have a for loop for I equals to 1, I less than square root of n, right? Square root of n and I plus plus. I less than equal to square root of n and I plus plus. Right? Now I will check if in fact n is divisible by I. So what should I print over here? If n is divisible by I should print I, right? I should print I. But is that all? Is that all? No, because I also have to print the other pair. Right? Remember, we are only going to half the pairs down. So we also have to print the other pair. So I will also print n divided by I. Right? N divided by I. Right? And that will complete the list of factors. Is this part clear? Yes? Perfect. Right? Now, first of all, there is a mistake in this program. There is a mistake in this program, a very subtle mistake. Can someone point that out? Yes? Exactly. So over here, let me just point it out. So over here, Lucky says that, hey, this is the mistake, right? What happens when I is actually equal to n by I? Which means that when n is a perfect square, you will be printing this number 2 times, right? That is not very good. You will be printing this 2 times. That is not very good. So how can we fix this? Right. So first of all, is everyone clear? If n is 9, n equals to 9, what we will see? We will see I equals to 1. We will print 1, 9. Right. I equals to 2. We will not print anything. I equals to 3. We will print 3, 3. Right. So we see that we printed 3 2 times. That is not a good thing to do. Right. So we need to resolve this. And we see that this only occurs when n is a perfect square. Right? Otherwise, this issue cannot occur. Right? So how do we resolve this? We simply say that I goes till less than square root of n. Right? I goes till less than square root of n. And after this, we will specially check. After this loop is over, we will check. So after this loop, what will be the value of I? It will be exactly square root of n, if it exists. Right? So we will say if n mod I equals to 0, then print it just once. Right? Print it just once because it is a square root. So just print I. Right? Notice that we are not printing the pair over here. Is that clear? Cool. So this will give us the correct answer. Now the question is, how much time did we save? What is the time complexity? What is the time complexity of this particular code? Yes. So who can tell me that? Well, this is very simple, right? Just like the previous case, we have a simple for loop. And this for loop now goes from 1 all the way till square root of n. So the time complexity is supposed to be order of square root of n. Right? Simple. Is that clear? There is one more thing over here, that if you were actually using a function to calculate the square root of n, you would not do this again and again. Right? You will actually say sqrt or square root equals to, you will calculate the square root of n outside. Square root of n outside, and then you will just use that variable. Right? So that whenever you hit this condition, you don't have to calculate it again and again and again. Okay? So this will give us the correct code, and the complexity will be order of square root of n. Now that is a huge improvement. Right? That is a huge improvement, going from order of n to order of square root n. This is huge. This is massive. Imagine that you had a number which was, let's say, 100 trillion. Right? 100 trillion. 100 trillion is how much? 100 trillion is how much? It is 10 to the power 14. Right? If you were to check this number, if you were to check a number of this order of magnitude on your computer, it will take a lot of time. Right? How much time will it take? It will take around 10 to the power 5 seconds. Right? Or you can say it will take around 30 hours. It will take around 30 hours of time. Whereas with this particular algorithm, how much time will it take? It will take just 10 to the power 7 operations. So this is 10 to the power 7, square root of 10 to the power 14 is 10 to the power 7. So it will just take how much time? It will take 0.01 seconds. Right? That is amazing. We went from a program that took 30 hours to a program that ran in 1/100th of a second. All right? Cool. So this is how we would factorize a particular number. Okay. So I hope this is clear to everyone. Now let us move on to a question, right? To a question, related question. Okay. Suppose that we have 100 doors, right? And all these doors are closed. All are closed. So we have basically door number 1 over here, door 2, door 3, door 4, all the way till 98, 99, 100. Right? We have all these different doors, and initially all of them are closed. So let me say that these are closed. Okay. Now we are going to play a game. We are going to play a game. This game will have 100 steps because we have 100 doors. We will have 100 steps. So the first step, what will we do? We will toggle all the doors. Right? So you understand what toggle means, right? Toggle means that if it is open, you close it. On the other hand, if it is closed, you open it. Toggle basically means to flip it. Right? Cool. So we will say that in the first step, we will toggle all the doors. In the second step, we will toggle all the doors, all the even doors. Basically, we will toggle every second door. Every second door. Right? In the third step, we will toggle every third door. And so on and so forth. It will continue like this forever. In the 100th step, we will toggle. So there will be just 100, right? We will toggle the 100th door. Right? So this is what we are going to do. Is this part clear? So first of all, what happens after the first step? Initially, all of them are closed. After the first step, all of them will be open. Right? Then what will happen? After the second step, we will toggle this every second door once again. So this door will become closed. 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 Right? In the third step, we will once again toggle every third door. So this third door will become closed. There was a sixth door over here. Right? It was initially closed. So we will open it up. Right? And so on and so forth. Does that make sense? So we are doing this thing. That is the game we are playing. The question is that after we are done with this game, after 100 steps, which doors remain open? All right. Is the question clear? Yes, after the third step, we will toggle every fourth. So in the fourth step, we will toggle every fourth door. In the ith step, we will toggle every ith door. Right? And the question is, after all these 100 steps, which doors will remain open? Okay. All right. So, I mean, this 100 is a very, very large number, right? So let us actually reduce the problem. So whenever you have a difficult problem, you try to check that problem on smaller numbers, right? So let us say that we only have 10 doors. Okay, we only have 10 doors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Initially, all of them are closed. Okay. What happens after the first step? So this is the 0th step. This is step 0. Step 1, step 2, step 3, step 4, 5, 6, 7, 8, 9, 10. Right? What happens after the first step? After the first step, every door is open. Right? After the second step, what happens? After the second step, what happens? So after the second step, 1 is open, 2 is closed, 3 is open, 4 is closed, 5 is open, 6 is closed. Right? 7, 9, these are closed now. What happens in the third step? In the third step, 1, we do not change it. 2, we do not change it. 3 was open, right? 3 was open, so we will close it. 4, we do not touch it. 5, we do not touch it. 6 was closed, so we will open it. 7, we do not touch. 7 remains as it is. 8, we do not touch. 9 was open, so we will close it. 10, we do not touch. Yes? Okay, we move on. So in the fourth step, we will keep 1. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this, and we will not touch this. And so on and so forth. So can someone see what is happening over here? Can someone see what is happening over here? Basically, what happens in the ith step? What happens in the ith step? Exactly. So Srinivas has the right idea over here. Srinivas says that in the ith step, all the doors that are divisible by I, get toggled. Right? That is the problem over here. Now the question is, let us suppose that I am talking about the nth door. Right? Let us suppose that I am talking about the nth door. For which all numbers, for which all steps will toggle this door? Will toggle this door. Right? So is the question clear? If in the ith step, I toggle every ith door, then given a door number, right? Given that I am saying that, okay, let's talk about the 20th door. Right? Let's talk about the 20th door. Then in which all steps will this 20th door be toggled? In which all steps will this 20th door be toggled? All the factors of n. Exactly. Right? All the factors of n. Yes. So basically 20th door will be toggled in the first step, in the second step, fourth step, fifth step, 10th and 20th step. Is that clear? Yes, because these are all the factors of 20. Cool. So how many times will this door be toggled? How many times will this door be toggled? Well, we already know that factors come in pairs. Right? Which means that if there is a step number 1 on which this is toggled, there is also a step number 20 on which there is toggle. Right? Similarly, for step number 2, we have step number 10. For step number 4, we have step number 5. Right? So we know that the nth door will be always toggled, an even number of times. Right? Because why is this true? Because the factors will come in pairs. Right? So every door is going to be toggled an even number of times. Is that correct? Well, not so fast. Is there any particular number which has an odd number of factors? Right? What happens? So you have this pairs coming up. Right? You have these pairs coming up. What if there is a middle value? What if n is a perfect square? In that case, this value root n, it doesn't have a pair. Right? Root n is going to pair with itself. So it will not have a pair. So basically, if the nth door, So if n is a perfect square, right? If n is a perfect square, then nth door will be toggled an odd number of times, right? In all other cases, it will be toggled an even number of times. Is that clear? Yes. All right. Cool. So what happens if you toggle a door even number of times? Initially, it was closed. Then it became open. Then it became closed. Then it became open. If we do this an even number of times, what will the end state be? It will be closed, right? Because we started with closed, we toggled it even number of times, so eventually it will be closed. On the other hand, when n is a perfect square, we will toggle it odd number of times. So what will be the final state? We started with closed, we move to open, we move to close. Since we will do this odd number of times, the final state will be open, right? So which all doors will be open? Now we know the answer. Which all doors will be open? All the doors whose numbers are perfect squares. Perfect squares, right? And in all the doors from 1 to 100, which all doors are those? Which all doors are those? So that is 1, then 4, 9, 16, 25, 36. Then what do we have? 49, 64, 81, and 100. Right? Exactly 10 doors will remain open, and all these are the doors that will remain open. Is that clear? No. If n is prime, the answer will be even. So Vishwajit has a question over here. Vishwajit says that if n is prime, then how many factors does it have? Well, for any prime number, it has two factors, right? 1 and n itself. So for prime numbers, it will be even, not odd. Only for perfect squares. Only for perfect squares will we have odd number of factors. Odd number of factors. All right? Cool. Okay. So what did we learn from this particular problem? This was not a very difficult problem, right? This also does not involve a lot of programming. We did not do anything fancy. We did not do any fancy maths over here. All we did was we sat down, we made some observations, right? We made some observations. We looked at the problem, we tried it with a smaller number. Instead of going to directly 100, we tried it with a smaller number. So that is something that you have to keep in mind, right? Whenever you're facing a problem, whenever you're facing an algorithmic problem or any problem in life, please, your first step should not be to come up with a solution. That is a very, very wrong way of doing things. The first step should be to make observations. Make observations. Right? Once you do this, only then you will be able to find a solution. Find a solution. If you do not make observations, you will never be able to find a solution. All right? So please do not skip this step. Okay. Cool. So that was a nice little exercise. Let us go back to what we were doing earlier. Right? So first of all, what we did was we found all the factors. Found all the factors of n. Right? That is the first thing that we did. Now, while we were doing this, we kept talking about something, right? We kept talking about prime numbers. So first of all, can someone quickly tell me what a prime number is? So what is the definition of a prime number? What is the definition of a prime number? A prime number, so first of all, it has to be a positive and it has to be an integer. Right? It has to be a positive integer. Secondly, it must have exactly 2 divisors. Right? It must have exactly 2 divisors. There is a lot of people think that this is the definition of prime numbers, right? A lot of people think that a prime number is a number which is divisible by 1 and itself. Right? By 1 and itself. If this was the definition of prime numbers, then 1 would be a prime number. Right? Then 1 would be a prime number because, hey, 1 is divisible by 1 and 1 is divisible by itself. But 1 is not a prime number. All right? Is that clear? So this is not the correct definition. This is very close, but this is not the correct definition. The correct definition is that it must have exactly 2 divisors. Exactly 2 distinct divisors. Right? So can someone very quickly tell me what the prime numbers are? A few prime numbers from the start. So is 0 prime? Is 0 prime? No, it is not. Is 1 prime? No, it is not. Is 2 prime? Yes, 2 is prime. 2 is the smallest prime number. Then 3 is prime. 4 is not prime. 5 is prime. 6 is not prime. 7 is prime. 8 is not prime. 9 is not prime. 10 is not prime. 11 is prime, and so on. Right? How many prime numbers are there? How many prime numbers are there? 100, 200, 500, 1000, million, billion. How many prime numbers are there? There are infinitely many prime numbers. Infinitely many prime numbers, right? Everyone knows this? Cool. There's a very simple proof for this as well. All right. Okay. So now that we know the definition of a prime number, some people are saying 4 prime numbers are there. That's nice. Suppose now that we know the definition of prime numbers, can we write a program? Can we check if a number is prime? Right? So we know that the definition of prime number is a number which has exactly 2 divisors and it is a positive integer. So given a number, can we check if it is prime? So is prime, right? It is going to return a boolean and it is going to take an integer. Yes. So how can we write this program? So very simple, right? Very simple. We can say that count is 0, right? We can write a loop for I equals to 1, I less than equal to n, I plus plus, right? And we can check if n mod I equals to 0, then we will do count plus plus, right? And finally we will return what? If the count is exactly equal to 2, then it is prime, otherwise it is not prime. Yes? Right? Cool. What is the time complexity of this program? What is the time complexity of this program? This program runs in order of n time. We already know that we can optimize this a lot. Right? We already know that we can So Suraj says why boolean? So this is prime will return true or false, right? It will return true or false. True if the number is prime, false if it is not. Right? Which is why we are returning a boolean. TechGeos is asking, sir, just confirming, is this code Java, right? So this might not exactly be Java. For example, in Java, you will have to put a semicolon over here, right? I'm not sure if you write bool or boolean in Java. I kind of forgot, but the rest of it pretty much looks like Java, right? Pretty much looks like Java if we add these semicolons. This will also work in C++, almost exactly the same way, right? However, when we are doing these classes, we will not be following any particular programming language. If you have any questions of a particular programming language, that let's say if you want to ask, okay, how will I do this in Rust, or how will I do this in Haskell, or how will I do this in, let's say, Python, right? So you feel free to ask that. Okay, feel free to ask that. I will be able to give you an answer for most common programming languages. However, we will not be focusing on the programming language in this particular class, right? We will be focusing on the pseudocode. We will be focusing on the intuition. Okay, cool. Okay, all right. So we see that this is linear in time, but we already know that we can improve this a lot, right? So how can we improve this? Instead of going from 1 to n, we can go from, so if 1 is a factor, right? If n is a factor, right? And prime numbers have exactly 2 factors. What does this mean? What does this mean? This means that if n is prime, if n is in fact prime, then it must not have any factor, between 2 all the way till n minus 1. Yes? Is that clear? It must not have any factor between 2 all the way till n minus 1. In fact, it must not have any factor between 2 all the way till n by 2. In fact, we can even generalize this and we can say that a prime number does not have any factors between 2 all the way till square root of n, right? Because we see that the factors will come in pairs. Right? The factors will come in pairs. Is that clear? So we can improve this code a lot. We can say Boolean is prime is prime, right? We have an integer n, and we will say, so now we don't need that count anymore, right? Because we are just checking if there is a prime factor or not, if there's a factor or not. So we can say for I goes from 2 all the way till square root of n, I plus plus, right? If there is any factor, if n mod I equals to 0, if we did find a factor, then what can we say? If we did find a factor, then what can we say? Hey, we found a factor, so it must not be prime. If you found a factor between 2 and square root of n, it cannot be prime. So we'll just return false. Return false over here. Right? And after this loop is done, we will return true. Because if we did not find any factors except for 1 and n, then the number must be prime. Is this clear? And the time complexity of this code is? The time complexity of this code is order of square root of n. Right? Perfect. So we know that we can check if a number is prime in order of n time as well. Now, one question, it's not, I mean, we are not going to teach that today in the class, but one very common question is this the fastest we can do? Is this the fastest we can do? And the answer is no. The answer is no. In fact, primality testing, this is in P, right? This is in P. P stands for the polynomial time algorithms, right? I'm not sure if you have heard of P versus NP, right? But primality testing is in P. That means that we can check for primality in log n time, right? In order of log n time. All right, we will not be going over this particular algorithm today. So there are several algorithms. One of the most famous ones is the AKS primality test, right? Okay, but primality can be checked in order of log n. It is in P, right? And no, this is different from sieve of Eratosthenes. Right? This is different from the sieve algorithm. This is a different thing. Okay. So if someone asks you how much time does it take to check if a number is prime, the answer is log n. Right? You can test primality in polynomial time. Okay. Cool. Vikas says, what if n equals to 5? So Vikas has a question over here. Let us look at this code and see what happens when n equals to 5. Does this code work correctly? Right. So let us try that. So what happens? So first of all, we will say I equals to 2, right? So we will first come over here. We will check I equals to 2. Then we will move on to the condition. We will move on to this condition, right? That is how a for loop works. We initialize, we check the condition, we go inside the block, we increment, and we check the condition again, right? So we will check this condition. Well, what is the square root of 5? The square root of 5 is? Well, the square root of 5 is 2 point something, right? Let us suppose that we are doing integer things over here. So we will say that, okay, this is 2 is less than equal to 2.5, right? Less than equal to 2 point something. So we will go inside, right? We will go inside. We will check. Is n divisible by 2? Is 5 divisible by 2? No, it is not, right? So we will continue the loop. We will increment I. I will now become 3. Now once again we will check. Is 3 less than equal to square root of n? No, 3 is not less than equal to square root of n, right? 3 is greater than square root of n. So we will exit this loop and we will return true. So we will say that yes, 5 is prime, which is correct. Okay. Okay, so there's another question. Santosh says that, okay, what if 2? What if we check with n equals to 2? Right? What happens when n equals to 2? Won't this program return false? Let us see, right? So when n equals to 2, we start, right? We start with I equals to 2. Right? Then we move on to the condition. We check if 2 is less than equal to square root of 2. Is this true? Is 2 less than equal to square root of 2? No, it is not true. Right? This is not true. So it will directly come outside the loop. Okay, it will directly jump outside the loop. It will not go in the loop. And we will return true. So even for true, we will return true. Is that clear, Santosh? Yes. But this program is not 100% correct. This program is not 100% correct. Can you tell me one value for which this program will fail? Exactly. So Ayush has the right idea over here. What if n equals to 1? Or what if n equals to 0? Or what if n equals to minus 100? Right? For all the numbers that are less than 2, for all the numbers that are less than 2, we will never go inside this loop. So we will automatically return true, right? So we need to improve on this program. We need to improve on this program. We need to add a check over here. Right? So let me just insert some space. So we will very quickly, let me just clear up the mess. This was square root of n. So we will add a check over here. We will check if n is less than or equal to 1, then we simply return false. Right? We simply return false. All right? Is this clear? No, this is not a base case. Base case happens when you are in a recursion. Right? Base case, we talk about base cases when we are in a recursion. This is a edge case. This is a boundary condition. Okay? So it's almost the same, but it is better if we follow the correct nomenclature. Okay? Base case is when we talk about recursion. Currently, we're talking about edge cases or boundary condition. All right. Yes, we can also say that this is less than 2. Right? We can, instead of saying less than equal to 1, we can also say less than 2. That is perfectly fine. All right. Okay. Let us continue. So now we know how to check if a number is prime. Now a very common question comes up. Let me just check how we are doing on time. All right. So a very common question comes up now, which is called if you had to find all the primes till n. Right? So I give you a very, very large number n, let us say 1 million. Right? And I ask you, find out all the primes till 1 million. Right? How will we do that? Is the question clear? We have to find all the primes till 1 million or some number n. So one way of doing that is to very simply go through all the numbers and check if they are prime. Right? So we can simply do for I equals to 1, I less than equal to n, I plus plus, right? And we will say if is prime. If is prime of I, right? So this is prime is the function that we have coded earlier. If this is prime is the function that we have coded earlier, we will simply print I. Simple enough? Yes. How much time will this algorithm take? How much time will this algorithm take? Well, this is prime function. This takes order of square root of I. Right? This takes order of square root of I. And we are doing this thing n times. Right? We are doing this thing n times. So how much time does it take? It definitely takes, it is bounded by, it is upper bounded by, so the time complexity of this program is upper bounded by order of n times square root of n. Right? N times square root of n. It is a little lesser than that, but as importantly, this is what the type bound is. Okay? Cool. Can we do better? Now the question is, can we do better? This was the simple approach. We had the program, we had this function is prime that we have already coded, right? And we simply say, okay, let us go through all the numbers and let us check them. So this will take this much time. The question is, can we do better? All right? Cool. So the answer to this is yes, right? In general, yes. There is something called sieve algorithms. Sieve algorithms. All right? And there's a lot of different sieve algorithms. So one of the most famous that you will come across is the sieve of Eratosthenes, right? The sieve of Eratosthenes. And this is how you pronounce the name. You say Eratosthenes. Okay? Eratosthenes. So this sieve algorithm can achieve much better time complexity. All right? Now, let us continue this particular thing in tomorrow's class. All right? We are going to keep the today's class simple enough because you will have a lot of practice problems that you can go and try it. We will talk about this sieve algorithm tomorrow. And this is a very elegant algorithm. This is a very nice algorithm. It is also very simple to code. Right? So it only has like 5 to 6 lines of code. And that gives you a very powerful algorithm that checks, that finds all the numbers, all the prime numbers up to a given number. All right? Cool. So one thing that Ankush is pointing out over here, or not this, where did that comment go? Interesting. That comment just vanished. Yes. So Ankush is pointing out over here that in this particular program that you wrote, right? In this particular program that you wrote, You write this loop as I equals to 2 all the way till square root of n. We can rewrite this in this manner as well, right? So I'm just pointing it out over here, as Ankush said, that these two loops are equivalent. I equals to 2, I is less than equal to square root of n, right? I plus plus. This loop is the exact same as this loop for I equals to 2. I times I is less than equal to n, I plus plus. Okay, so instead of calculating the square root of n and then comparing it with I, we square I and then we compare it with n. Right? It will work exactly the same. And this is one more way that you can do it. If you were to do it this way, then you will have to pre-calculate the square root of n, right? You will say square root of n equals to, you will use some sort of a math library. You will say math.square root of n and things like that. So if you do not want to do that, you can simply use I into I is less than equal to n. All right? Bridge says, but don't we have to check for overflow? Well, not really, Bridge, because I into I will not overflow, right? If I into I overflows, then n itself should overflow. Does that make sense? We are not really considering the overflow case over here. We're talking about not too big numbers. Okay, we are talking about numbers that will fit in the integers. Now, if n fits in your memory, if n fits in let's say a 64-bit integer, then I into I will also fit in 64-bit integer. All right. Srinivas says, sir, how to deal with very, very big numbers? Well, Srinivas, there are a lot of different ways that you can tackle big numbers. One very common approach is to use a big integer library, right? Big integer library, right? But usually this is not a very good approach, right? First of all, the question is, why would you need to deal with big numbers, right? If you are implementing, let us suppose, some sort of an RSA algorithm, and you want to check if a number is prime or not, then you might have other ways of generating large prime numbers. Right? In practice, we don't really have to deal with we don't have to check very large prime numbers with something like a sieve. Right? With something like a sieve, we don't do that. Okay. So let us end the class. Once again, please subscribe to the channel, hit the bell icon so that you can be notified of the videos. And in the next class itself, we will be going over prime numbers once again, and we will be going over a lot of different things. So we have to cover GCD. So greatest common divisor, Euclid's algorithm for that. We have to cover model arithmetic and a lot of different topics. All right. So please make sure that you subscribe to the channel, hit the bell icon, and please go and practice the problems.
Hello, everyone. So in the last class, Pragya has taught you about how to check whether a number is prime or not. Okay. So is everyone clear with that? If given a number n, can you all check whether the number is prime or not? Now, once you know that whether a number is prime or not, now let's try to modify the problem a bit. Okay, so instead of getting a direct problem of checking whether a given number is prime or not, let's say that you have to print first n prime numbers. Okay, given a number n, you have to print the first n prime numbers. Or another question could be that you have to print all the prime numbers less than n. Another question would be that you have to print all the prime numbers in the range from L to R. Okay. So these are the three types of questions which we are going to solve optimally in today's class. Okay. Now, if you all remember, if when you have to check whether a given number is prime or not, what is the time complexity of that operation? You are going to run a loop that starts from 2, goes till square root n, right? And with every number in this range, you try to divide n and you see whether n is divisible by that number or not. If n is divisible by none of the numbers, then you can say that n is prime. So the time complexity of this operation is order square root n, right? Now, if you have to check, if you have to print the first n prime numbers, what will be the time complexity of this approach? If you have to print first n prime numbers, you will be checking for all the possible numbers, right? You will run a loop for all numbers from 1 to n. And then you will run another loop. Maybe you will have to increase the size of the first loop because first n prime numbers might exceed n as well, right? So the time complexity of this is going to be n root n, right? For each and every number, you will be checking, you will be running a square root n check, right? Similarly, if you have to print all the prime numbers which are less than n, again, the same time complexity will be there, n root n. If you have to print all the prime numbers in the range from L to R, then again, size of range multiplied by square root n. So all these types of questions can be solved in this time complexity and into square root n using a very easy check prime algorithm that we have learned in the previous class. Okay, can we do it optimally? Can we do something to make all these problems easy for the computer? Now there is a very, very well researched algorithm, with very famous algorithm, which many of you are already writing in the comment. It's called the Sieves algorithm, right? So in today's class, we are going to learn about the Sieves algorithm. Okay, do you guys understand what is a sieve? What is the literal meaning of a sieve? If you just translate sieve in Hindi, what is that? It is nothing but a channi, right? This is chai sante hai ghar pe. So it has a net, very fine net, and a handle. Right? This is a sieve, right? And printing all the prime numbers using a sieve is going to be exactly same as how you filter your tea. Okay, we'll see how. So जब चाय छानते हैं तब क्या होता है? You have a utensil, right? In this utensil you have the cooked chai, right? And then you pour it on the sieves, and after this you have your tea mug, right? So at this point, this complete mixture is called chai, right? At this point you say that everything which is there in the utensil is my chai. But when it is filtered, then whatever is in your teacup is called chai, right? तो पहले तो जो उसमें था पूरे को हमने बोल दिया कि यार ये चाय है, चाय बन गई है, इसको छान लेते हैं. जब छन के आई तो फिर हमने बोला यार चाय तो ये है, ये जो इसमें रह गया है ये चाय नहीं है, ये चाय पत्ती है, अदरक है, जो भी है, चाय नहीं है, है ना? So sieves is going to function in an exact same way. We have to figure out what are the prime numbers. We'll say that all the numbers are prime, right? So we'll take all the numbers and we'll say that all of them are prime. Then we will pass them through a sieves. After passing them through the sieves, we will see that only the actual prime numbers are remaining. All the composite numbers will be filtered out by the sieves. Okay, let us see how it is going to work. So first of all, let us write down all the numbers on which we'll be running the sieves. Okay, so we have all these numbers. Initially, just like the T, I'm saying that all of them are prime. Okay, all the numbers are prime. Now for 1, we are very sure that 1 is not a prime, right? Is everyone clear with this thing that 1 is not a prime, right? Why is 1 not a prime? Because a prime number has to have exactly 2 divisors. 1 has got only exactly 1 divisor. So 1 is not a prime, so we can directly remove 1. Okay. Now, whatever is the first number which is present in this in the list of all these numbers, which is available in the list, we'll say that this number is a prime number. Okay. So what is the first available number here? The first available number is 2. So I'm saying that 2 is a prime number. So we'll filter out 2. 2 comes out of the seeds. Okay. So we have poured all the numbers here till 40, and now 2 has fallen. 2 has been successfully, he has crossed the seeds. Okay, 1 has stuck here. Now if 2 is a prime number, can I say that all the multiples of 2 will never be a prime number, right? Because all the multiples of 2 will definitely have 1 as a divisor, themselves as the divisor, and also 2 as a divisor. So they are not satisfying the criteria of being a prime number. Does this thing make sense to everyone? Does this thing sounds obvious to everyone? That any multiple of 2 can never be a prime number, right? So if any multiple of 2 can never be a prime number, so what can we do? Filter them out, cut them. So I will just cut all the multiples of 2 which are present in this list. So 4 is gone, 6 is gone, 8 is gone, 10 is gone, right? So all these multiples are removed from this list. These all have been filtered out and thrown away. What is the next available number which is there in the seeds? What is the next number that I can see? The next number is 3. So I can say that, okay, 3 is also a prime number. Let's add 3 as well. Okay. Once I am declaring that 3 is a prime number, can I say that any multiple of 3 does not stand a chance for being a prime number? Any multiple of 3 is always and always going to be a composite number, right? So let us filter them out. Let us remove them from the list. So let us remove all the multiples of 3. 6 has already been removed. Then we remove 9. 12 has already been removed. We remove 15. 18 is already gone, right? And then 21. 24 is gone. 27. And then 33. 36 is already gone. Then 39. Okay. Now, which number is the next available number in this list? The next available number is 5, right? So I can say that 5 is also a prime number. Okay. So out of all these numbers, we have till now filtered out 3 numbers which are prime numbers, right? So now 5 has come. So any multiple of 5 will never be a prime number. So all the multiples of 5 will also be removed. So currently I can see that all the multiples of 5 have already been removed. 10 is gone, 15 is gone, 20 is already gone, 25 is remaining. So we'll remove 25 as well, and then 35. Okay. Then what is the next available number in this list? The next available number here is 7. So 7 becomes the next prime number. Okay. And all the multiples of 7 will also be removed. So now 14 is gone, 21 is gone, 28 is gone. All the multiples of 7 have already been removed. Okay. What is the next available number that we have? Now we have 11. So 11 becomes the next prime number. And all the multiples of 11 again have already been removed. Then we have 13. Then we have 17. Then we have 19. Then we have 23. Then we have 29. Then we have 31, 37. And that's it. So now you can see that we have got all the prime numbers in the range from 1 to 40. These are all the prime numbers in the range. All the prime numbers which are less than 40 are now with us. Is the idea of the algorithm make sense to everyone? Is the idea clear? How the algorithm is going to work? Initially, we said that all the numbers are prime numbers. Assume that all of them are prime numbers. Pass them through the sieves. What does the sieve do for us? The sieves algorithm takes the first available number and declares it a prime number. So we declared that 2 is a prime number. Since 2 is prime number, none of its multiple can be a prime number. Cut them out, remove them. Then take whichever is the next available number, call it a prime number, remove all the multiples of this number as well. Okay. Now let's try to see how can we write the code for this. Okay, the code is going to be very, very small, very, very easy. Right. So what we are doing here is initially what we are doing is we said that let us first take all the numbers. So if let's say we have to print all the prime numbers in the range n, so then we take an array prime of size n plus 1, because if n is 40, array indices are going to start from 0. So I also need 40 as an index. So I will take the size as n plus 1. Okay. And I will say that all of them are prime. Okay. So this prime array, what does it hold? This prime array, for every index, it holds true or false based on whether the number is prime or not. Right. So currently I am saying that if this is my array. Okay. Currently I am saying that all of them are prime. So have true for each and every index. Okay. Then what we will do is we'll first declare some of the already known values, right? So we know that 0 is not a prime. So we can say that prime of 0 is false. So this will be turned false. And we also know that prime of 1 is also not a prime, right? So 1 will also be converted to false. Now starting from 2 to n, we have to check each and every number whether they are prime or not. So how did we do this in this algorithm? We selected whichever is the first true value. Basically, the first available means the first true value, which is currently declared as a prime number, right? So we'll run a loop which will start from 2, and this loop will go till n, and we'll be incrementing the value of I one by one. And then we have to check whether this value has been removed or not. So if it has not been removed, then we will always be having a true value. Okay. So we'll just check if this number at index I, if it is true, if this number is currently a prime or not. What is the first available prime number that we have here? Right? If it is a prime number, this means that none of its multiple can be a prime number. So for all its multiple, make them false. So if 2 is true, 4, 6, 8, 10, all these numbers should be turned to false. So I will just run a loop. Let's take a different variable. So now what we have to do for I, we have to make 2i, 3i, 4i, all these numbers as false, right? So we'll quickly run a loop starting from 2, and we'll see till where we have to run this loop, and then do this. We'll say prime of I into j, right? So I is already there. This is our j, right? This has to be false. So we till what value we have to increase j? We don't know, right? We don't know that. So we actually don't know till when we should be incrementing j. But what we know is that this product, this 3i, 4i or ji, this can never be greater than the maximum value that we have. So this product can never be greater than n. This always has to be less than or equal to n, right? So here what we'll have is j into I is less than or equal to n. Okay, because if you see in this list, when you select I is equal to 2, then from where to where your j ranges, j starts from 2. So if j is equal to 2, you cut 4, then j becomes 3, you cut 6, j becomes 4, you cut 8, and you will go till 40, right? So j becomes 20. You don't want to increase j such that you are trying to cut a number which is greater than 40. So always we are keeping I into j less than or equal to n. Okay, cool. Now let us see. Let us try to quickly see what happens when we are actually cutting the numbers, right? So when my I takes a value 11, okay, when I'm taking a value 11, in this case, when we selected 11, what was the first number that we tried to cut? The first number that we tried to cut was 11 into 2, which is 22, right? So if I is 11, we are going to check it for value of j is equal to 2, right? Which will give us 22. Then we will try to cut 33. Then we will try to cut 44. Then we will try to cut 55 and so on. Then j will become 11 and we'll cut 121 and so on, right? Now I have a question. When I'm trying to cut all these numbers for the value of I equals to 11, can I say that 22, 33, 44, 55, all these numbers would have already been cut? Because before I takes the value 11, I will also take the value 2. When I takes the value 2, 22 would have been cut by that, right? So you must have observed in this case also that when we reach to 11, all the multiples of 11 were already cut, right? When we reached to 5, what was the first number that we cut? 10 was already gone using 2. 15 was already gone using 3. 20 was already gone using 2. What was the first number that we cut using 5? It was 25. If I start from 11, then we can see that none of the multiple of 11 is available here, which has not been cut. All the numbers have been already cut, right? Why that happened? Because before taking a value 11, I must have taken all the values which are less than 11. So all those values have already been cut. So 22 has been cut by 2, 33 has been cut by 3, 44 has already been cut by 2, 55 has been cut by 5, and so on, right? So what should be the first value from where we should be starting the second loop? From where we should start the second loop? This has to start from j is equal to I, right? Because when we were trying to cut the numbers from 5, we saw that the first number that we are cutting is 25. Similarly, for 11, the first number which will be available there is going to be 121. All the other numbers must have been cut by the smaller values of I. So we don't need to start from 2, we can start j from I, okay? Now, if we are starting j from I, what is the maximum value that I can take? Do we need to run the first loop till n? Okay, let us try to analyze the second loop, and that will give you the answer whether we should be running the first loop till n or not. Should it go till n by 2? So what is the maximum value that we have to cut? The maximum value that we have to cut is here 40, right? Okay, and whenever you are starting to cut, you are always starting from the I value, which means that the first value that you are cutting is I square, right? For 2, you are cutting, the first value that is being cut is 4, right? For 3, the first value that you are cutting is 9. For 5, the first value that you are cutting is 25. For 6, the first value that you will be cutting is, for 6, you will anyhow won't cut any value. For 7, what will be the first value that you will be cutting? For 7, the first value should be 49. 7 into 7 is 49. Is 49 in this range? No, 49 is out of this range. So what should be the maximum value? The maximum value till which we can go is I square. So I can never go beyond square root n, right? Because the first number that you are cutting here, like this number, which is the last number, would have been cut when I becomes square root n, right? So this n can be turned to square root n, right? So either you can say I is less than or equal to square root n, but if you are using this function square root n, this is an expensive operation of finding a square root of a number is actually expensive operation. It will take at least log n time. So what you can do is you can replace this by I into I less than equal to n. So now you are doing the checking order 1 operation. This is going to take log n time, at least if you are printing the integer part, right, using binary search. Okay. So now let us come to the time complexity. Okay. This loop, the first loop is running from 2 to square root of n. Let us actually remove all the optimizations that we have done. We'll try to calculate a very relaxed upper bound. Okay. So tell me one thing. When the value of I is equal to 2, how many times does the inner loop run? If let us say that this starts from 2, if we are considering the previous loop, the totally unoptimized loop, which was starting from 2 and going till n, and this loop is also going till n, we are considering the most unoptimized version. Now tell me, if value of I is equal to 2, how many times are we going to run this loop? This loop will start from 2, go till n by 2, right? We'll be cutting exactly n by 2 numbers. For I is equal to 3, how many times is the inner loop going to run? The inner loop is going to run for n by 3 times. For I equals to 4, how many times is the inner loop going to run? For I equals to 4, is it going to run for n by 4 times? For I equals to 4. So see what happens is when I takes a value 2, we cut 4. We say that now 4 is not a prime because 4 is a multiple of 2. And before running this loop, we are always checking whether I is prime or not. Is 4 a prime? No, 4 is not a prime. So this loop, the inner loop, is going to run how many times? Exactly 0 times. This if case is going to fail for 4, right? For 5, it is going to run for n by 5 times. For 6, this is going to run for, again, 0 times. 6 is not a prime. For 7, this is going to run for n by 7 times, right? So can you see a pattern here? If we have to add all these time complexities, what will we get? We'll be getting n by 2 plus n by 3 plus n by 5 plus n by 7 and so on. What are these? If you take n common from here, you get 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus 1 by 11 plus 1 by 13 and so on. What are all these? These are nothing but sum of reciprocals of prime numbers, right? First n prime numbers basically, correct? So I can say this is equal to I equals to 1 to n 1 by p. All the prime numbers, the first n prime numbers, or maybe all the prime numbers which are less than n, right? All the prime numbers which are less than n. This is the time complexity. Now, if you are really good at mathematics, you will be able to, you will be knowing that this whole sum can be approximated to log of n. Okay, so this is the overall time complexity of Seed's algorithm. Okay, so if you are really good, or if you are interested in mathematics, you can read about the Merton's theorem, which proves this thing. Okay, that sum of reciprocal of first n prime numbers is same as log of n. So the overall time complexity can be approximated as order of n into log of n. Okay. Okay, I will quickly brief over the time complexity part once again. Okay, so if we are just checking for every value of I, how many times is the inner loop going to run? Okay, so I said that if I is equal to 2, how many times is the inner loop going to run? Inner loop is going to start from 2. We are assuming the most unoptimized version. We are removing all the optimizations that we had done. So inner loop will start from 2 and it will run for n by 2 times, right? If you are starting from 2 and you have to go till 40, you will be running 20 times, right? You will cut 20 numbers in this loop. Similarly, for I equals to 3, you will be running the inner loop for n by 3 times. For I equals to 4, now this is a very important thing, that before running the inner loop, you always check whether this number is prime or not. 4 is not a prime. So for 4, the inner loop will never run. For I equals to 5, the loop runs for n by 5. Then for 6, again, since 6 is composite, loop does not run. Then for I equals to 7, loop runs for n by 7 and so on. So if you add all of them, right, because when you have to calculate the time complexity, you will be adding how many times the inner loop is running in total, right? And that will be the overall time complexity. So if you add all of them, you get this series. Here, if you take n common, then you get something which is nothing but the sum of reciprocal of all the prime numbers. And if you apply Merton's theorem, if you are aware about the Merton's theorem, you will be knowing that sum of reciprocal of all the prime numbers can be approximated as log of n. So that is why the time complexity of Siev's algorithm is order of n log of n. Okay. Now this is the most relaxed time complexity that we have achieved because we removed all the optimizations, right? The optimization that says that the first loop should run only till square root of time. This loop should start from I. We have removed all of them and then we have calculated. So whatever, if you do any optimization here, your algo is definitely going to be better than this time complexity. Okay. The question is, will this work for a range whose first element is not a prime number? This is only going to work if you are starting it from 2. If you are starting from any random number, this algorithm is never going to work, right? Because you have to make sure that all the composite numbers are cut. So if let's say if you are trying to find the numbers in the range from 40 to 100, right? So you have these numbers, and now if you start cutting the numbers from 40, you're trying to cut the multiples of 40. This is not what Sieves is suggesting. Sieves is saying, give me the first prime number. What is the first prime number? First prime number is 2. Cut all the multiples of the first prime number, not the first prime number in this range, the first prime number overall, right? So you will always be starting, or this algorithm will only work if you are starting cutting the numbers from 2. However, if you have to find the numbers in a range, what you can do is you can pre-compute all the prime numbers. So what you can do is, if you have what would be the maximum value of range, then starting from 2 to that range, you can pre-compute all the prime numbers. Okay. Once you have all the prime numbers in this range, now what you can do is you can this array is going to be a sorted array, so you can apply binary search and you can find all the positions of the lth prime number and rth prime number and print all the values. Okay. Cool. Is the Sieves algorithm clear to everyone, including the idea, the intuition, and the code? Is everything clear to everyone? Great. Now what we'll do is we'll try to see a problem. Okay. So we still have 30 minutes. So we'll try to solve a very, very good problem, which is a very commonly asked problem and a very generic problem. Okay. The problem says that given a number, return the prime factorization of this number. What is prime factorization? So is everyone here clear with the thing that any composite number can be written as the multiple of all prime numbers? Not all prime numbers, but multiple of prime numbers. Is everyone clear with this thing? So if I give you n is equal to 24, what would be the prime factorization of 24? 24 can be written as 2 into 2 into 2 into 3. Basically 8 3s are 24, right? So 8 is nothing but 2 raised to power 3. So 24 can be written as this. So the prime factorization of 24 would be 2, 2, 2, and 3. This is what you have to return. Okay, is the problem clear to everyone? If the value of n, let's say, is 10, you will be returning 2 into 5. Okay. If the value of n, let's say, is 42, then we have 2, 3, and 7. Okay. Is the problem clear to everyone? Given a number n, you have to return the prime factorization of n. Prime factorization means you have to represent that number in terms of only prime numbers, and that is possible for each and every number, right? Because any number either will be a prime number or a composite number. If it is a composite number, you can further divide it into prime numbers, right? For example, if n is 24, you can write it as 2 to 2 into 3. There can be many ways. Can there be many ways? Varun, just try to think and figure out. Can there be many ways? If you are breaking down the number into prime numbers, not composite number, none of the numbers in the returned array should be a composite number. Okay, what can be? What is the first thing that comes to the mind? So if let's say I'm given 24 and I have to, so we must have done this in schools, right? We all have done the prime factorization of the number in school in the elementary mathematics, right? This was, I think, in 6th class maybe or 5th class when we learned about the prime numbers, right? So how did we used to do it at that time? So if I'm given 24, what will I try to do? I will pick what is the smallest number with which I can divide it, right? So the smallest number that I can figure out is 2. So I will try to divide 24 with 2. I get 12, okay? And this 2 gets added to my answer. Now I have got 12 and I know that again I have to do the exact same thing. Find the smallest number with which I can divide this, and that number obviously should be greater than 1, right? So again, here also the smallest number that I can think of is 2. So I divide it with 2, I get 6. Again, I can divide it with 2, so I get 3. Now 3, the smallest number that can divide 3, bigger than 1 is 3, so I get finally 1. All these numbers are definitely going to be a prime number because we are always selecting the smallest number, right? If that smallest number is not a prime number, then there must be a number which is smaller than this that can divide this number. Does this make sense to everyone? What I'm trying to say is, if there is a number x, which is the smallest number, which is dividing 24, and x is not a prime number. If it is not a prime number, then it must be a composite number, and then it can be broken down into 2 prime numbers, at least, right? So 24 will also be divisible by these 2. So that means x was not the smallest number that can divide it. There are smaller number than x which can divide 24. So using this proof by contradiction, I can always say that the smallest number which is able to divide any number is going to be a prime number. Okay. Now, how to code this thing? I'm just going to code the same approach that we used in our 5th, 6th class mathematics, right? So to do this, first we can initialize an answer array or maybe a prime factor array. And what we are going to do is, so here in this case, I just used my mind and saw that this is divisible by 2. But for computer, we'll have to check with every number starting from 2, right? What is the first number that divides 24? And then keep dividing it by that number till it is divisible, right? So I will start from 2 and I will say that this has to go till somewhere and then I plus plus, and then I will say while this is divisible, if it is not divisible, then it will not go inside the loop. But if it is divisible, first of all, add this I to the answer. So we'll do prime fact dot add I. Okay, add this to the answer and then divide n. So n will become n by I. Okay. So what we are doing in this case is n is initially 24, right? We are starting from I, and we are and the first value of I is 2. So we are checking if it is divisible. If it is divisible, then keep dividing it till it is divisible. So we divide it, make it 12, n becomes 12. Then the loop still checks that this is still divisible by 2. So keep dividing it, and also keep adding it to the answer. So the answer will have 2, then in the next step again 2, and then again 2. Then you have 3. So this will break out because now n mod 3 is not divisible. Sorry, n mod 2 is not divisible. N has now become 3, right? 3 mod 2 is not equal to 0. So we'll increment the value of I. So I now becomes 3. So then we'll check n mod 3 is now divisible. So we'll add 3 to this and we'll divide n further. So now n becomes 1. Okay. So the question is, till when this loop should run? What should be the breaking condition here? What can be the maximum number that I can take? The maximum number that I can take is, we may use set instead of array. No, you cannot take set because set will guarantee that the occurrence of every number will be limited to exactly once, whereas we need 3 2s. If you are taking a set, you will have exactly 1 2, right? So set is not useful in this case. You'll have to take a list, array list or array which supports multiple occurrences of same character, right? Okay, so what should be the maximum value that I can take? The maximum value that I can take obviously is going to be square root of n, right? So the I that we are going to increment is going to be till square root of n. Okay. Now this code is going to print all the prime factors for us. I can see that there are 2 mistakes in this code, 2 very big mistakes. Can you guys quickly figure out them? This code has 2 blunders, and one of them is the most commonly done mistake while writing a code. Even when people write the most simplest of the codes, they make this type of mistakes. Can you quickly figure that out? It doesn't work for 0 and 1. Yes, so this is guaranteed in the input that n will always be greater than 1, because even the person who is asking the question knows that 0 and 1 will not be are not eligible for this question. Okay. Right, so I can see that one of the mistake has been pointed out. The other mistake no one is able to guess. Let us see what we are doing. Let us quickly reiterate over the code. We are saying that I is starting from 2. I should go. What is the maximum limit that I is taking? It is taking square root of n. So here, instead of this, I would be writing what? Actual square root of n. Or maybe to keep it optimized, let us have I into I less than equal to n. Right? This is the more optimized version of the same thing. Okay. So what we are doing here is we are initializing I. We are checking that I should not go more than square root of n. And inside this loop, what we are doing is we are changing the value of n. Correct? N is changed inside this loop. N is also there in the breaking condition. So initially, we started this loop with an assumption that n is going to be 24. So the maximum value that I can take is going to be root 24. In the next iteration, you changed n to 12. So this loop here, now this condition is not going to hold true because n has been changed. This is the most common mistake that I have seen students doing while writing most easiest of the codes. If you are changing a value inside the loop, you should never be taking it in the breaking condition. So always do one thing, assign some variable, this value, and then use it here. Okay. Otherwise, you will see your code behaving in very unexpected way, and you will not be able to realize what is going wrong there. Okay. So assign the value and then keep it inside the loop. This is one mistake. What is the other mistake? The other mistake most of you have already pointed out, which is if the number is already prime, right? If the number is already prime, or maybe number is having a prime factor which is greater than square root of n, right? If a number is having a prime factor which is greater than square root of n, for example, let us talk about 404. Okay. So for 404, how will this loop run? We'll start from 2. We check that 404 is divisible by 2. We divide it. Okay. Then we again check that this is again divisible by 2. We divide it. Now this is not. So we have added 2 and 2 in the array. Now this is not divisible by 2. Then this is not divisible by 3. And what would be the maximum value of that I will be taking in case of 404? The maximum value that I can take is going to be 20, right? Because the square of 21 is going to be greater than 404, right? So the maximum value of I is going to be 20, but we can see that for all these values of I, the prime factorization of 404 is not complete, right? So what we can say in this case, right? Because this is not complete. 101 would also have been there, correct? So this is another mistake in this code. How to fix that mistake? Can I say that even after removing all the possible prime factors from that number, if I have got a number which is greater than 1, that number must be a prime number? Can I say this? So to actually fix this code, can I just add another if condition? It says that if this number is still not reduced to 1, that means that this number has to be a prime number. So directly add this remaining number as well. So what we'll do here is if n greater than 1, then prime factor dot add n. We'll add this line here itself after the for loop completes. So if this number is not been reduced to 1, we will add 101 as well, and we will get the correct answer. Does this make sense to everyone? So this is about prime factorization. What is going to be the time complexity here? What is the time complexity of this code? So calculating the time complexity is pretty easy here, right? The first loop runs for how many times? The first loop runs for root n time. Okay. Then the second loop runs for, the second loop is going to run for how many times? We are dividing the number n by I every time in every iteration. So how many times the second loop is going to run? The second loop is going to run for log n time. So what should be the time complexity? Is it going to be root n into log n? Is the time complexity going to be root n into log n? No, right? This is wrong. This is not going to be root n multiplied by log n. Okay. Why? We can quickly see that this loop runs for root n times, and here we are dividing the number by I every time. In the worst case, the value of I is going to be 2. So in the worst case, if you're dividing n by I, how many times can you divide it? If given a number, how many times can you divide that by 2? This is given by log, right? This is given by log of 16. Log, whatever is the value of log of 16, you can divide 16 that many times by 2, right? But this is incorrect. Why? So let us try to analyze what is going on here. So if we have a value, let's say, let's take 16 itself. Okay, so in the first iteration, when the value of I is equal to 2, we check that this is divisible and we divide it. So we get 8. Then again we divide it by 2, we get 4. Again we divide it by 2, we get 2. Again we divide it by 2, we get 1. Okay. Now after we have divided completely with 2, for the next value of I, which is equal to 3, how many times is the inner loop going to run? For 3, how many times is the inner loop going to run? 0 times, right? Inner loop is not going to run because this has already been reduced to 1. Okay. If this has already been reduced to 1, now this inner loop will never run again. If this inner loop is not going to run again, for 3, number of iterations are going to be 0. For 4, the number of iterations are going to be 0, right? So what is the total number of times, including all i's, the inner loop is running? For all the i's, the inner loop is going to run for log n time. This is not for each and every I. This is for all the i's combined. For 2, it runs for log base 2n. Then for 3, it runs for log base 3n if n is there, right? So if let us talk about any other number. So if I talk about 24, 2 can reduce it to 12, then 2 can reduce it to 6, then 2 can reduce it to 3. Now 3 is not going to have log base 3 24, these many steps, because 3 is going to reduce this number, which has already been reduced by 2, right? So the total number of steps, including all the i's combined, is going to be log of n. So this is going to be log of n plus square root of n, which is nothing but square root of n. So the time complexity of this algorithm is going to be exactly square root of n, not root n log n. Okay, guys, in mathematics, there are multiple topics which are very, very important for programming point of view, or both the interview point of view as well, right? So there is modular arithmetic that you must learn, and you must solve multiple problems on this. Okay, then there is GCD, the LCM and HCF problems. Okay, GCD is also very, very important concept. Okay, then of course you definitely have the prime numbers, and in the prime numbers you can also optimize this approach that we have discussed, right? You can optimize this approach using a concept called the smallest prime factor of a number, which is called the SPF, which we haven't discussed in the class, but this is also a very important concept. Okay, so after the class, please go through this. What is SPF and how you can actually optimize this algorithm using the smallest prime factor. Okay, and then in the modular arithmetics, there is also Fermat theorem, which is very important. So just Google all these concepts and go through all of them. Try to solve problem based on all of them. Okay, they all are very, very important. They will help you in problem solving as well as in interviews. Okay, cool. So this is it for today's class. If you liked the video, if you understood everything, please like, please share it with your friends. Please tell us in comment which all topics you would want us to discuss next. Okay, tomorrow's class is going to be on bit manipulation. So if possible, before joining the class, if you can go through how numbers are represented, or what are the basic bit operations, then the class will go very smoothly, right? So next class is going to be on bit manipulation. So just read about some bitwise operators like OR, AND, XOR, left shift, right shift, etc. Just read about them. And if you found this video useful, you can just like it and share it with your friends. Okay.
Hello everyone, in this video we will study about arrays and its fundamentals. Arrays is basically a simple data structure that can also be used to build complex or composite data structures like stacks and queues. In this video we will discuss about arrays, and we will see what all different operations can be performed using arrays and how arrays are stored in computers' memory. So let's start with the definition of arrays. Arrays is a collection or systematic arrangement of objects of same data types. Data types can be integer, character, double, etc. Now let's say if we want to declare an integer array, then let's see how we will do that. We will first write the data type, then the variable name, and then the size of the array. So this is the data type, which can be character, float, double, etc. This is the variable name, and this is the size of the array. Now let's see where the concept of array is useful in computer programming. So let's take a case where we have to store marks of 10 students in the class, and we have to find the average marks of all the students in the class. So if we use the integer variables, we can have 10 different integer variables, m1, m2, m3, m4 and so on up till m10, where each variable corresponds to the marks of the student in the class. And in order to find the average, first we need to find the sum of marks, which can be calculated using m1 plus m2 plus m3 plus m4 and so on up till m10. Then we can easily find the average using the formula sum divided the size, that is 10 in our case because the class has 10 students. Now let's say instead of 10 students, if we have 100 students in the class, then you can easily see that it will be very difficult to have 100 different variables. So instead of that, we can easily form an array of data type integer and size 100. We know the indexing of the array starts from 0. So m0 will represent the marks of first student in the class, m1 will represent the marks of second student in the class, m2 will represent the marks of third student in the class up till m99, which will represent the marks of 100th student in the class. Also, you can see that to find the sum using m0 plus m1 plus m2 up till m99 will also not be a good idea. So instead of that, we can easily run a for loop, and let's see. So first we will have sum array, which will be initialized to 0. Then we can run a for loop, which is starting from 0 and going till 99. And we can easily update sum as sum plus marks of ith student. And in order to find the average, we can again use the same formula, which is sum divided by total number of students in the class, which is 100. You can clearly see that it will work even if the class has 1000 students or even more than that. So this is a clear example how arrays are very useful. We can also have arrays of different data types. So in this case, we are declaring an array of integer data type, but we can also have arrays of character, float, and so on of different data types. And also this is an example of one-dimensional array, but we can have arrays of 2-dimension, 3-dimension, and so on. Now let us see how arrays are stored in computer's memory. So computer memory is divided into segments or partition, and computer memory can be considered as a very large array of bytes. So each segment is representing 1 byte of memory. And in computer architecture, each byte of memory has an address. So we can assume the bottommost address is 0. Then as we go up, we have address 1, address 2, and so on. So let's take address of this byte as 100, then this as 101, then this as 102, and so on. In C and C++, we also have pointer variables that can store these address. Now let us take our array again. So we have an array of data type integer, and let's take the size 5. We know the size of integer is 4 bytes, and the total number of elements in our array is 5, and every element is having 4 bytes. So total size of the array becomes 20 bytes. Now when the program executes, the computer will allocate 20 bytes to this array. So you can assume that this 4 bytes will be given to A of 0 and computer will give continuous segments. So basically array of 1 will definitely have these 4 bytes, array of 2 will have above this, and so on. Now since memory allocation is continuous, so access and modification of the array element becomes very easy, and the access or modification of the array element takes order of 1 time. That is order of 1 time complexity. Now let us see how. So basically arrays A is also known as the pointer to the first element of the array. And A also represents the base address. So let us see using a C program how we can see the value of address and the value stored at that particular address. So let us go to a C program and let's declare the integer array of size 5. Now if you will execute this statement, printf %d is used for integers, \n is used for next line, and you will try to print A, this will print the base address or the address of first element of the array. And also if you will try to print the value at this address, which will also be an integer, you know, in C we can print the values using x star. So star A will print the value of first element of the array. Now we see that we have only declared the array. We have not initialized the array. So at this point of time, this will print a garbage value or any random value. So if we want to test it properly, let's also initialize the array. So array of 0, let's make it equal to 2. Array of 1, let's make it equal to 4. Array of 2, let's make it equal to 5. Array of 3, let's make it equal to 8. And array of 1, let's make it equal to 1. Now if you will print this again, the base address will be printed, but the value will not be any random value. Instead, this will print 2, which is the value of the first element of the array or the index 0. Now, if you will try to execute a statement like this, that is the address of the next element, that is A plus 1, this will give you the address of the next element, that is second element. Now, let's say if the value of base address is 100, this will return the value 104. Why? Because this is a pointer to the first element of the array, that is base address, and this is known as the offset. Now offset increase the address of the base address by the size of the data type. In our case, we are using an integer variable. Integer has size 4 bytes. So this will increase the address by 4 bytes. So if the base was 100, in this case 104 will be printed. Now as we mentioned, the SS is in order of 1. So let's say if we have to print the second value or the value of second element, we can easily run this, which will be an integer because we are having an integer array. An asterisk sign we know is used to print the value of particular address. So this statement will print the value of the second element, which we can clearly see is 4 in our case. Now, SS is order of 1 because, as we have seen, when we want to try or we want to find any element in the array, the address is calculated using base address plus the offset. So let's take an example. If we have to find the value of the third element of the array, we can either write it like this, that is value basically of the fourth element, which is the third index, and it can also be seen like this, that is base address plus the offset and the value at that offset. Now please note that the pointer arithmetics only applies in C and C++ because Java do not support pointer variables, but the internal working will be similar. So this was the basics of arrays and how they are stored in memory. In coming videos, we will study more about arrays. So I hope this video was helpful and thank you everyone.
So my name is Kshitij and I will be discussing about arrays in today's class. Okay. So in today's class, we are going to discuss some challenging problems on arrays, which can be solved just by the knowledge of arrays. In tomorrow's class, we'll be discussing some more challenging problems on 2D arrays, and then in the upcoming classes, we'll be discussing about sorting. Okay. So in the next 4 or 5 classes, we'll be discussing about arrays and sorting algorithms. Okay. So before we start the class, I just want your opinion on have you guys ever worked with arrays? Have you guys ever used arrays? Are you guys familiar with what is an array? Arrays are nothing but collection of same type of data, right? You can have an array of integers, you can have an array of strings, you can have an array of floating point data structure, or you can even have an array of objects, right? So array is nothing but a collection of data, and arrays, all the values in the arrays are stored in continuous memory locations, right? So if you have an array A of size 5, and if this is your memory, all these array elements are going to be stored in continuous memory chunks, right? So they are always in a sequence. Correct. Homogeneous collection of data. Absolutely correct. Okay. Now, in today's class, we are going to see some of the problems which do not require any algorithm, which do not require knowledge of any other data structure other than arrays. Okay. And these problems have been asked in Google, they have been asked in Facebook, they have been asked in Amazon. So if you are just familiar with arrays and if you have a basic logic building or problem solving skills, you can attempt these problems. Okay. Right. So regarding the language, so most of you are asking in which language are we going to discuss the problems, right? So let's keep the session language agnostic. Okay, we'll be discussing the logic, we will be discussing the pseudocode, but all the logics that we are going to discuss, they will be language agnostic. So whether you are coding with C, C++, Java, Python, Ruby, doesn't matter. You can apply those logics, you can apply the same solution in any language. Okay, so keep things language agnostic and let's focus on the problem solving techniques. Okay, one more thing guys, that with the class you will also be getting the problems that we are going to discuss. You will get the exact same problems, you will also get some variations of these problems. Okay, so that you can test your knowledge there, right? So I strongly recommend all of you to attempt those problems, because if you are just listening in the class and you feel that you have understood everything, you might understand things, but after a while you will forget. So it's always better to reinforce your knowledge by practicing those problems. Okay, so I will strongly recommend you guys to solve all the problems which are provided in the description link. Okay, cool. So let us start this session with a very, very interesting problem. And this problem was asked in Amazon. This has been asked in Facebook. This has been asked in Google. Okay, the problem says that you are given an array, and in this array you you are having heights of some buildings. Okay, so you can consider that these are 2D buildings, two-dimensional buildings with a width of size 1, and the height is given to you in an array. Okay, so let's say that this is the array in which you have all the heights of the buildings. Okay, now you can see this picture. So these are the buildings, right? And these black bars are the buildings, and it's raining heavily in this city. So you have got some clouds, and it's actually raining heavily. And because of the rain, there is some water which is being trapped between the buildings. Okay, so these are the clouds, not so good looking clouds, but yes, there are clouds. And you can see some water being trapped in between the buildings. So given the heights of the buildings, you have to identify what is the total amount of water which is being trapped in between these buildings. Okay, is the problem making sense? तो आप लोगों को एरे में बिल्डिंग्स या बार्स की हाइट दिए हुए हैं, एंड वहां पे शहर में बहुत तेज बारिश हो रही है, तो चूंकि ये 2 डायमेंशनल वर्ल्ड है, यहाँ पर कुछ वाटर ट्रैप हो रहा है इन बिल्डिंग्स के बीच में. ओके, आपको बताना है कि टोटल कितना अमाउंट है वाटर का जो कि ट्रैप हो रहा है. ओके, राइट, दिस इज अ वेरी वेरी फेमस प्रॉब्लम. इट इज कॉल्ड ट्रैपिंग रेन वाटर. This is a problem which is present in each and every platform. This is in LeetCode, this is in InterviewBit, this is in Geeks for Geeks, this is in HackerRank. This is present in each and every platform because this is very very frequently asked problem, right? So what is the answer for this case? Here we can see that 6 units of water is being trapped, right? 1 unit here, then you have 1 unit here, 1 unit here. So let's actually draw the squares, right? This is 1 unit of water. Then you have 1 unit of water here. Then you have 1 unit of water here, 1 unit here, 1 unit here, and 1 unit here. Right? So you have got 6 units of water being trapped between these buildings here. Okay. Now the question is that given the array, you have to identify, you have to calculate the total amount. Okay. How to approach this problem? Okay. So there is focus on what is contributing to the total amount. How do we calculate the total amount? So how have we counted the total amount of water in this case? To count the total amount of water, what have we done? We have just counted what is the amount of water trapped above each and every bar, right? So if I count what is the total amount of water trapped above each and every bar, and if I just add that, that would be the answer. For example, here this bar length is 0, so this bar is having 0 amount of water trapped. Here the bar length is 1, but even then the amount of water trapped above it is 0. Here the amount of water trapped above this bar of length 0 is 1. Right? Similarly, here we have 0 amount of water. Above this bar we have 1 unit of water, right? Similarly, above this bar we have 2 units of water. Here we have 1, then again 0, 0, then 1, 0, and 0. So if we just add all of these, we'll get the answer. If we just add the amount of water or the size of the water column trapped above each and every building, we get the answer. Now the question is how to get the amount of water trapped above each and every bar. Right? So we have reduced the problem from finding the total amount of water to count what is the amount of water trapped above each and every bar. But how to do that? Okay, again, let's make some more observations here. Okay, so we have seen that the amount trapped above this bar is 0. Okay, why is this amount 0? Why is it not non-zero? Why is this amount? Why is this bar not able to trap any amount of water above it? Simple reason is that there is nothing on the left side to hold the water, right? There is something on the right side, but if the water falls here, there is nothing on the left to hold it. Right? If there had been a bar on the left side, then you would be getting some water here, but there is nothing on the left side. So you can just consider this as a vessel which is of this L shape, right? You can consider this scenario as a L-shaped vessel. If you fill any liquid inside a L-shaped vessel, it will just flow from here, right? You cannot trap the liquid in a vessel which does not have the boundary, right? So that's why here we have zero amount of water. Now, what about this bar? This also has zero amount of water. What is the reason for that? This is not one. This has to be 0. What is the reason for this? Again, the same reason. This bar also does not have anything on the left side to hold the water, right? That's why this is also not trapping anything. When we come to this bar has got a size 0, but it is able to trap a water column of height 1. Simple reason being, it has got something on the left and something on the right as well. So now this is forming a complete vessel, right? So it can hold water, a water column of size 1. Now we come to this bar again. This has got a bar which is on the left side, right? If I'm talking about this bar here, this has got a bar on the left side. Even after that, this bar is not able to hold any water. Why? Because the bar which we have on the left side has got a smaller height, right? If you have to hold some water above this bar, you need something on the left and something on the right of a higher height, right? So you can assume that this is the surface of your vessel. Now, this bar here is below the surface, right? So you need something which is higher the surface. Then only you can trap some water inside this, correct? So that is why this is also not able to trap anything. Now, when you come here, this has got something on the left and something on the right as well, correct? So one thing which is very clear from this observation is that to trap the water, you definitely need something on the left side, something on the right side of a higher height than the current bar, right? This bar is not able to trap because it doesn't have anything on the left. This bar is able to trap because it has a support on the left side as well as on the right side. So it has got both the boundaries, correct? Cool. Now the question is, how do we, so we have determined that some of the bars will not be able to hold, but the bars which are holding the water, how much water is going to be there, okay? Now, to do that, to actually analyze that, let's consider a very simple example first, okay? So let's say that the heights of the bars are 2, 1, and 3. So we have got a bar of size 2, then we have got a bar of size 1, and then we have got a bar of size 3. And we are talking about this middle bar. We have to identify what is the amount of water being trapped above this middle bar, okay? This has got height 2, this has got height 1, this has got height. Can you guys quickly respond? What is the amount of water which will be trapped above this bar? The size of the water column here. Is it going to be 1? Is it going to be 2? Is it going to be 3? It's going to be 1, right? Why 1? Because the height on the left side is, this height is of size 2, right? And we have this bar till height 1. So the only limited space that we have for the water is this column. Anything above it will flow from here, correct? Okay, let's change the example. Let's add some more bars here. Okay, so initially we have this configuration where we have bar of size 2, 1, and 3. Now I am going to add one more bar on the left side. And this bar is also of length 3. Now, how much water will be trapped above this bar? Is it still going to be 1? Or now will we have some more water here? Yes, it's going to be 2 this time. Why? Because now we have got a higher support on the left side, right? So if it is continuously raining, all this area will be filled with water, right? And now we can see that this column, the height of this column has now become 2, right? The height of the water column trapped above the above this bar has now become 2. Height of the water column above this bar has now become 2. Okay. Why has it become 2? In this case, it was 1. Now it has become 2. What is the reason? what is the reason? The reason is the addition of this bar, right? Let's add some more bars, okay? Let us add some more bars to this configuration. So I will be adding a bar on the left side. Let's raise a bar of size 4. Will the height of the water column stored above this will increase? If I have just added a bar on the right side of length 4, will the height of the water column above this bar, is it going to increase? No, right? Because on the left side, it is still 3. On the left side, the maximum that we can have is still 3. Anything above it is going to flow from here. If we also add another bar of size 4 on the left side as well, now will it increase? Yes, now it's going to increase because from both the sides we have got a height of size 4, right? So is this complete observation making sense to you guys? The height of the water column stored above any height is nothing but the minimum of the maximum height that you can get on the left side and the maximum height that you can get on the right side, correct? The height of the water column stored above this is minimum of maximum height available on right and maximum height available on the left. So if I have to identify what is the height of this column, right? Height of water column above bar I, this is equal to, this is nothing but the minimum of maximum bar on left side, maximum bar on right side, minus the height of bar I. So if I am talking about, if this is my ith bar, the water column trapped above this bar is how much? This is minimum of maximum of left, maximum of right, minus the height of this current bar. If I have to calculate the total amount of water, this is just going to be the sum of all such values, correct? So the answer that we are going to calculate, sum of this value for each and every height, right? Sum of minimum of left max, right max, minus height of bar. So I will be calculating the minimum of left max, minimum and right max for each and every bar, subtract the height of that bar and keep adding it. So whatever we get at the end is going to be the answer, correct? Let's quickly do this thing on the given example, right? What is the minimum? What is the minimum on the left side for this? Minimum on the left side for the first bar is 0. There is nothing on the left. Sorry, maximum on the left side, right? Maximum on the right side is this bar of length 3. But since we are taking the minimum of left max and right max, minimum becomes 0. 0 minus the height of the bar is 0, right? So this is not going to hold anything. What about the first one? Again, left max is minimum. Left max is 0. So we won't be getting anything, right? For this bar, for this water column, the left max is 1, right? The right max is 3. So minimum of left and right is 1 minus the height of this bar, which is 0. So this is going to hold 1 unit of water, right? So if we do the same thing for each and every bar, we are going to get the answer. Let's also see for this column. So here, what is the left max? Left max has got a height 2. Right max has got a height 3. Minimum of 2 and 3 is 2. Right? So this bar is going to hold 2 minus the height of this, which is 0, this much amount of water. So we just have to do this thing for each and every bar, and we add whatever amount is trapped over that bar, and we get the answer. Okay. Okay, let's do this in this example. Let me just clean it up a bit. Let's try to calculate what is the total amount of water that will be trapped in this scenario. Okay, if this is the landscape of the buildings that we have, what will be the total amount of water trapped here? Okay, so we are saying that the total amount of water trapped is the sum of water trapped above each and every building. What if negative? Heights are not going to be negative. right? Negative height means that you are digging a hole and then so it's basically kind of a plinth. So you can assume that such buildings with negative heights are not possible, okay? Okay, let's try to run our approach on this thing, okay, on this scenario. So for this building, what is the maximum height on left side? Maximum height on left is 0. Maximum height on right is 4. For the first building, the answer is going to be 0, right? For the second building, maximum height on right is 4. Maximum height on left is 4. Maximum height on right is also 4, right? So we'll be getting minimum of these two minus whatever is the height of the building, which is 3. So this is going to contribute 1 unit of water, okay? Then in the next building, so the 1 unit of water comes here. In the next building, we will be checking minimum of what is the left max. Left max is still 4. What is the right max? Right max is still 4. Building size is 2. So we get 2 units of water above this, okay? Similarly, for the next buildings, again, left max, right max are 4 and 4. Building height is 1. So we get 3 units of water above this. Okay. Similarly, we'll be doing for this as well and this as well. And once we add all these values, we'll be getting the answer. Okay. Cool. So now once this is clear to everyone, can you guys tell me what is going to be the time complexity of this approach? So for every bar, we are calculating a maximum on the left side. We are calculating the maximum on the right side. And then we are applying this observation and getting the height. What should be the time complexity if we go by this approach? Okay, let me just reiterate over this example again. For if I'm calculating for this bar, I will have to calculate what is the left maximum. To calculate the left maximum, I will be iterating over all the possible bars on the left side. To calculate the right maximum, I will be iterating over all possible bars on the right side. How much time is this operation going to take? This is going to take order n. How much time is this operation going to take? This is also going to take order n, right? So to calculate the water column above each and every bar, we are doing an order n operation because these two are going to get added, right? And we are going to do this operation for each and every bar. There are n bars in total. If there are n bars and for every bar, our calculation requires order n time complexity. What is going to be the total time complexity? Right? So there are n bars. For every bar, we are going to do order n operations. So the total time complexity is going to be order n squared. Okay. Can we optimize this order n time complexity? In the last class, you must have learned that order n is not a very good time complexity, right? Yes, Vijender, you are absolutely correct. Right, guys. So to optimize the time complexity, again, let's make a very, very simple observation, right? So till now, we have deduced that for every bar, we have to calculate the left max and the right max. Okay. Let's talk about the last bar. Okay. If I'm talking about the last bar, then we are calculating the left max for the last bar. How actually we calculate the maximum for this? The order and operation of the maximum, or finding the maximum. How do we run it? So we will be declaring a max, right? And we'll keep updating it after visiting each and every bar. So we'll initialize a maximum value. We can initialize it with a very with maybe minus infinity or maybe a not possible or 0. Maybe we can also initialize it with the length of the first bar. Okay, so we say that currently the maximum is this, and we'll keep updating the maximum as soon as we visit all the bars in this order n loop, right? So if let's actually take a complex example. So if the bars are of size 2, 3, 1, 4, 5, 2, 1, 7, okay, 2, 9. If these are the lengths of the bars, if I have to calculate the maximum from left for this last bar, right, I'll be starting from here. Okay, let's initialize the maximum with 0. Okay, so we are saying that whatever is the maximum between the current maximum and the current bar is going to become the maximum, right? So maximum is initialized by 0. When we reach here, we say that 2 is the maximum. Then when we reach here at 3, we compare this value with the current maximum, right? This is how we calculate the maximum of an array, correct? So we calculate current value of the array with the current maximum. So 3 becomes the maximum. Then we compare this 1 with the current max. Let's call it the current max, okay? Again, 3 remains the maximum, so we'll fill 3 here. So this means that till this point, 3 has got the maximum height, right? Now similarly, for the next step, we'll be comparing 4 with 3, okay? So this gives us 4 as the maximum, then it gives 5, and then we'll be having 5, 5 till this point. Then we get 7, and then 7 continues to here. So the maximum on the left side for this bar is 7, okay? Now in this process, if you have observed, what have we done? We have not only computed the max for the last bar, but we have also computed the left max for each and every bar. So if you just store all these values in an array, instead of just keeping a variable of the current max, if you just have an array and store all these values inside the array, these values are corresponding to the maximum height on the left side for each and every index. Is this making sense? Till this point, 5 is the maximum. Till this point, again 5 is the maximum, right? Till this point, 7 is the maximum. So while you are calculating the maximum value for the last bar, you have not only calculated the maximum on left for the last, but you have also calculated the maximum for each and every index. So in a single iteration, we have the values of left max for each and every value. Okay, let me just repeat. Let's clear each and everything here. Let's do it once again. Okay, so when we have to calculate the maximum on the left for the last bar, first of all, is everyone clear that we'll be calculating the left max for each and every bar and right max for each and every bar? Yes. Now, let's talk about this guy. Let's talk about this bar. If you have to calculate the left max, you will be iterating over this part of the array, right? You will maintain a left max for this bar, and you will keep updating that left max while visiting the array, right? You will initialize a left max with 0. You will check whether 0 is greater or this value is greater, right? So you will keep updating this left max while iterating over the array. Similarly, you will do the same thing for the right max as well, correct? Now let's talk about the last element. Let's not talk about the middle element. Let's talk about the last element. When we are doing it for the last element, we are actually calculating the left max for each and every index, right? Left max till now is 0, right? Or let's call it 2 here. So we have initialized the left max by 0. We compare it with 2. We get 2 here. Then we get 3 here, right? Then we get 3 again here. Then we get 4 here, 5 here. 5 continues till we get a longer height, which is 7, right? And again we get 7 here. What if 9 is not present? Then also you do the same thing. If 9 is not present, you have 1 bar less in your structure. Then when you calculate the left max for the last index, doesn't matter whether it is 9 or any other number. When you are calculating the left max for the last index, you have actually calculated the left max for each and every index in this process. The only thing is that you will have to store these values. Instead of updating the current max variable, if you just store these values in the array, you get the left max for each and every index. Similarly, while calculating the right max for this index, the first index, you will be calculating the right max for each and every value, correct? Because to calculate the right max for the first index, you will be iterating from the right side, and you will keep updating all the values one by one, right? So you start from here till now, the max is 2, then you get 7, and then 7 continues to be the max till now. Okay. So is this observation making sense? The observation is that we don't need to run this order n loop for each and every index, because when you are calculating the left max for the rightmost element and when you are calculating the right max for the leftmost element, you are essentially calculating each and every value which is required in this calculation. So instead of running these two loops of order n on each and every index, what we can do is we can just run a single loop and we can store all the required data. We can do some pre-computation. Okay. We need 2 extra arrays. Yes, we will be needing 2 extra arrays. Let's call this array as the left max array, and let's call this array as the right max array. Okay. If we have stored these values, can you guys now tell me what will be the amount of water stored over any ith index, stored over any ith bar? If I talk about this bar, what will be the answer? What will be the amount of water stored over this bar? We need the maximum bar. We need the maximum bar on the left side of this. From where can we get it? The maximum bar on left side of this bar is here, right? We have already calculated it. The maximum bar on the right side of this bar is present here. If we are talking about the ith index, the left max is stored at left max I minus 1, and the right max is stored at right max I plus 1. Okay, you don't need to run 2 loops for each and every number. We can just pre-compute the left max and right max for each and every index, and using these values, now we can have a different loop and we can get these values in order 1. Okay. What if we store in the ith index itself? Will that work? That will definitely work, Anushka. You will just have to check. Like you can also store for every ith index. You can store what is the left max height at this index and right max height at this index. You will just have to calculate. You will have to this. You will have to keep check on the corner cases. Okay. If you are able to keep checks on the corner cases, then that will also work. Okay, so let's quickly see the pseudocode. Okay, so we can have a left max array. Okay, what will be the size of this array? Size of the array is going to be same as the size of the input array, because for each and every index you want this information, right? So its size should be equal to n, whatever is the size of the input array, correct? And similarly, we'll also be having a right max array, which will store the right max for each and every bar. Okay. Then let us initialize these values. So we can say that left max of 0 can be initialized from the array 0. Okay, and right max of okay, let's come to the right max after we finish this, right? So we have initialized this for the 0th index. That means I'm saying that for 0th index, this is the answer. The height of the bar is the answer. Now for the remaining bars, we can just run a loop, which will start from some point, go till n, and we'll be doing it. From where should we start the loop? Should it start from 0? Should it start from any other number? Yes, the loop is going to start from index 1, because we have already filled the value on index 0. So we don't need to start from index 0. Okay. And for every index, we can say that left max of I is nothing but the maximum of the previous max, which is left max of I minus 1, and the current array value, the current height. So whatever is the maximum between the current height, right, between the current height and the previous is going to be the left max of this iteration. Okay. Similarly, for the next value of I, we'll be comparing this value and this value. Okay. So we have our left max array filled up. Now we'll also initialize the right max array. So for the right max array, how did we start? We started from the right side, right? We said that we are starting from here, and let's copy the array value, the last array value in the last index of the right max array, because for this value there is nothing on the right side. So we are starting from here. Okay. So right max of n minus 1 is going to be array of n minus 1. And now similarly we can have a loop which will also start from some number, go till 0, and this is going to run from right to left. So that's why we are doing I minus 1. So from where should we start it? This loop will start from n minus 1. We have already filled the value for n minus 1, right? So this should not start from n minus 1. N minus 1 is some value which is required to compute the value at this index. So we'll be starting from the index n minus 2. Right? To calculate the value here, we need to compare this value, which is the previously calculated value, and the current height. Okay. So let's go back here. We'll be starting this from n minus 2, and right max of I is going to be the maximum of what will come here? Yes, it should be I plus 1, because now when I'm checking for this index, I am comparing this value. If this is index I, this is I plus 1, not I minus 1. In case of left max, we were comparing with the previous index. Now we are comparing with the next index, right? So this is going to be right of I plus 1 and the current array value. Okay. So now we have got the left max and the right max array populated. Okay. Now we just have to run a single loop to calculate the total amount of water trapped. So you can have a variable water initialized with 0, and now we can run a loop, and this loop should run for each and every height. So we'll start from I equals to 0 less than n. We'll be incrementing the I with 1, and we can simply say keep adding the amount of water trapped over each and every bar in this variable. So water plus equals to, or you can also write it as water equals to water plus the, how do we calculate the height of water column? Minimum of left max, right max, right, minus the array value I. Cool. What is the time complexity of this approach? Time complexity of this is, see, first in this code, first we are populating the left max array. For each and every bar, we need what is the left max. So this is going to count order n, plus this array, this loop is also going to be of order n, plus this loop is also going to cost order n, right? So the total time complexity of this approach is order 3n, which asymptotically is same as order n, right? Order 3n is nothing but this is same as order n, because when you calculate the time complexity, you ignore the constants, right? Edge case missed, right? So if this is just a pseudocode, okay, now you have to attempt this problem, you have to solve it on your own, and in the code which you are writing, you have to take care of all the edge cases as well. Okay, Himanshu, that is on you now, so you have to do it on your own. Okay. What is the space complexity? Guys, can you tell me what is the space complexity? We are using two arrays of size n, right? So it is going to be order n in space as well. Okay, let's do one thing. Let me just tell you the problem. Okay. This is also a very, very interesting and very frequently asked problem, which is called the majority element. The problem says that you are given an array. You have to find the majority element in that array. The majority element is the element that occurs more than n by 2 times. Okay. which means that the number of times that element is occurring in the array should be strictly greater than n by 2. For example, if this is your array, 3, 3, 4, 2, 4, 4, 2, 4, 4. Can you guys quickly tell me what is the majority element in this array? N, which is the size of the array. What is the size of the array in this case? 9, right? Now, which is the element which is coming more than 9 by 2 times? Correct. Majority element in this case is 4, because 4 is occurring 5 times. Okay. 4 is the majority element here because 4 occurs 5 times. Let's take another example. Let's say we have 3, 3, 4, 2, 4, 4, 2, 4. What is the majority element in this case? Size of the array is 8. What is the majority element which is occurring more than 4 times in this case? 4 is occurring 4 times, right? But we need something which occurs more than n by 2 times. 4 is not more than 2. So in this case, we do not have any majority element. Okay? No majority element. So you have to, if there is a majority element, you have to return that element. If there is none, you can return none. Okay? This is the problem. Is the problem clear to everyone? What would be a brute force way to solve this problem? What if 2 elements are majority elements in the same array? Guys, that is a very, very interesting thing that Satyam has asked. Can there be 2 majority elements inside a single array? Satyam, think about it. Can there be 2 elements which are occurring more than n by 2 times? No, right? How 4 is greater? 4 is not greater than this, but the count of 4 is 5. Right? We have to count the number of times this element is occurring. We don't have to return the element which is greater than n by 2. We have to count the number which is occurring more than n by 2 times. Okay. Cool. So what is going to be the brute force solution here? Brute force solution is going to be simply you run 2 loops. For each and every element, you just check whether that element is a majority element or not. Select this element. In the remaining array, count the number of occurrences. If the total number of occurrences is greater than n by 2, return it. Otherwise, go to the next element. Check for this element in the remaining array. If it is occurring more than n by 2 times, return. What is going to be this time complexity of this approach? It's going to be order n square. Why? Because you are running 2 loops of size n. Correct? Okay, so brute force is not going to work. This is too slow. How can we optimize it? Using hash map, right? So some of you are saying that we can use hash maps. If you use a hash map, first of all, how can we solve this problem using a hash map? So this is a very, very good suggestion that use a. What is hash map? Is everyone clear with that? If you are not clear, you can skip this. If you are clear, you can think in this direction. Hash map is nothing but a key value pair, right? So you can have a key and you can have a value in the hash map. Now every array element becomes the key and the frequency becomes the value. So against 3, you keep 1. Then you again go to 3. You see that 3 has already occurred in the hash map. You increase the frequency. Okay. Then you go to 4. 4 is not occurred yet. You keep it and you put 1 here. So after you have iterated all the array, yes, it's totally like the dictionary in Python. Okay. After you have iterated all the array, you will be having all the array elements along with their frequencies. Okay. So 4 will be 5 at the end because the frequency of 4 is going to be 5. And the frequency of 3 is going to be 2 and 2 is also going to be 2. This is the value, the array element, and this is the frequency. After you have made this complete map, you can iterate over all the keys and you can figure out which of them is the majority element. This is one of the approach. What is going to be the time complexity of this approach? If you are not aware about what is a hash map, you can totally skip it. We will be covering hash map in details in the upcoming sessions. But if you are clear about hash map, then you can just think about what is the time complexity of this approach. This is going to be order and time complexity, correct? What is the space complexity here? You are using a hash map which is going to cost you order and space, right? Order and time complexity plus order and space complexity. Okay, you have to solve this problem in a linear time with constant space. Okay, this has to be your time complexity, this has to be your space complexity. Is the requirement clear to everyone? You cannot use a hash map. If you are not clear about the hash map approach, completely skip it, because this is something that you cannot use in the question. Okay, you have to solve this problem in order and time complexity, order one space complexity. Okay, think about it. This is going to be something which we'll discuss in the next class. Right, so in today's class, we'll first discuss the majority element question that we discussed in the last class, and then we'll solve one more problem which will be based on a two-dimensional array. Okay, so the problem that we left unsolved in the last class was that you are given an array and you have to find the majority element of that array. The problem says that you are given an array, and in this array you have to find the majority element. Okay, the majority element is an element which is occurring more than n by 2 times, more than n by 2, where n is the size of the array. Okay, so if the array size is 9, the element has to be there at least 5 times. Okay, it is possible that there is no majority element in the array, because there might be a possibility that there is no element which is occurring more than n by 2 times, right? Correct. So the brute force way to solve this problem as proposed by Sai is that you run 2 loops, and for every element you check the number of count of that element in the array, right? So you will start from the first element, you will select this element, then you will check in the remaining part what is the total occurrences of this element. Okay, you can then see if the total occurrences is greater than n by 2, you can return it. Then you will check for the next element, then you will check for the next element, and so on, right? So you will have 2 loops. One will be selecting a prospect candidate, the other will be checking if that element is a majority element or not. This approach is going to cost you order n square time. Okay, we discussed a more optimized approach also, which was involving a hash map. If you use a hash map, what will be the time complexity? If you use a hash map, since in hash map you can store a key value pair, right? So a hash map is nothing but a key value pair. If you are using Python, you can think in terms of a dictionary, right? So key can be your array element, and the value can be the frequency of that array element. So you iterate over the array once, and you keep the count of frequency of all the elements in this hash map. Once everything is done, or while calculating the frequency only, you can just check if there is an element which occurs more than n by 2 times. If any element occurs more than n by 2 times, then you can return it. Okay, so this approach is going to cost you order n time, but order n space as well, because you will be using hash map. Okay, how to create hash map in C? You can use unordered map in C. Now, the question here is that we have to solve this problem in order and time complexity without using any extra space. So we have to solve this problem in constant space complexity without using any extra space. Okay. Okay, so most of you are saying that now you will apply the Moore's voting algorithm, which is absolutely correct. Okay. Okay, we have one more approach. The other approach says that you first sort the array. If you sort the array, since the majority element is going to occur more than n by 2 times, right? And once you sort the array, all the similar elements will be arranged together, right? So some similar elements will be there. Then if there is a majority element, then it will also be there. And then some different elements of similar type will be arranged together. if there is an element which is occurring more than n by 2 times, once you have sorted this whole array, either you can do a linear iteration or maybe you can just check the middle element and check the count of that element as well, right? So if you sort the array, what will be the time complexity? If you are using the most efficient sorting algorithm, even after that, what is going to be the time complexity of sorting the array? It's going to be order n log n, right? You can use quick sort, merge sort, or heap sort, right? And all these sorts are going to run in order n log n time complexity. If you are not sure about all these sorting algorithms, you will be covering them in the upcoming classes. So don't worry about it. If you already are familiar with the sorting algorithms, then you can sort this array, and then you can iterate over the array and count the occurrences of all the distinct elements, right? So in that case, the time complexity is n log n, which is absolutely greater than order n, right? So this is again not an optimal approach. Okay, so let's discuss the idea behind the most optimal approach for this problem. Okay, let's try to change the perspective. So first, let's consider an example. Let's take this example only. Okay, so if there is a majority element, the question says that the majority element will be occurring more than n by 2 times, right? The count of majority element is always going to be greater than half the size of the array. If there exists a majority element, can I say that the collective counts of all the other elements will always be less than n by 2? If majority element exists, if there is a majority element, can we say that the count of all other elements combined will be less than n by 2? Obviously, yes, right? Because half of the array has been occupied by the majority element. If you collect all the majority elements together, starting from the 0th index, and if this is the n by 2 mark, the majority element will definitely occupy, starting from 0, it will go more than n by 2. Right? So the remaining space that is left in the array is obviously less than n by 2. Correct? Okay, now if this is the case, if everyone is convinced that the count of all the other elements combined is going to be less than n by 2, now let's try to see this whole scenario in terms of, let's say, election results. Okay, let's actually consider all these array elements as the results of an election, result of different constituencies. Okay, so these are different parties. This is a party 4, this is a party 3. Okay, and let's try to see in terms of the election results. Okay, so the party to which the majority element belongs, okay, in this case is going to have 1, 2, 3, 4, 5. 5 constituencies have been won by the majority element, right? And if we collect all the other elements together, this is going to be 1, 2, 3, 4. Okay, so we have some other element A and some other element B, right? So these are the results from different constituencies. These 5 constituencies have been won by the majority element, and all these are won by different candidates. Okay, so if you remember the 2019 general elections, there was a party BJP which was in majority, and then there was something called as Mahagathbandhan, right? So in Mahagathbandhan, there were various parties which they combined hands and they were fighting against BJP all together, right? So you can just assume that these all are the constituencies won by the Mahagathbandhan, and these all are the constituencies won by BJP. Now, if the election commission says that 2 out of all these constituencies are being disqualified, there has been some cheating in 2 of these constituencies, so we are removing the results. We are not counting the results of these 2 constituencies. So if the election commission says that one of BJP's constituency and one of the Mahagathbandhan's constituencies will not be counted in the election result, if these 2 are removed, who is going to win the election? two constituencies here are removed, who is the new winner? Initial winner was BJP, right? Now who is the new winner? You can quickly count the total votes and quickly see who is winning it again, right? It's still BJP, right? So what we have done, if you look in terms of this array, you have removed one occurrence of the majority element, and with that you have also removed one occurrence of a non-majority element, right? So we have reduced the size of the array by 2, and the occurrences of the majority element has been reduced by 1. Okay, let's say 2 more constituencies were removed. So one from BJP and one from Mahagathbandhan again were removed. Who is the winner? Who is the new winner now? It's again BJP, right? You can quickly see that it is still in majority. It is still having a size more than n by 2, right? So what we have done here is we have removed one occurrence of the majority element. With that, we have also removed one occurrence of a non-majority element. Okay. Again, if you do the same thing, you can see that BJP still remains in power. If you remove 2 more constituencies, we have only one constituency left, which is of BJP. So the idea is that if with every occurrence of the non-majority element, if you remove one occurrence of the majority element, at the end, you will be left with at least one occurrence of a majority element. So the idea here is that if I am removing one occurrence of any non-majority element with one occurrence of a majority element, the majority element still remains the same. Let's try to see it from other analogy as well. Okay, one another analogy could be that there are 2 countries, or let's say there are 3-4 countries, and 3 countries are fighting against one country combined. So there is a country C1, there are country C2 plus C3, and let's say C4. Okay, now C1 has got majority of soldiers, right? So the soldiers that C1 has, let's denote them as S. So let's say it has got 7 soldiers, okay? And all these other countries combined, okay, or let's say that, let's represent all these soldiers by I, okay? Then we have some more countries, and we have 3 soldiers in the country C, or let's say 4 soldiers in a country C. We have 2 soldiers in a country P, and we have 1 soldier in a country B. Okay. Now, since initially the number of soldiers in the country C1 have outnumbered all the soldiers in all the other countries combined. Now, if one soldier here dies with one soldier of any of these countries, who is going to have majority of the soldiers? Will that change? So initially C1 is in majority, right? Now, very similar to what we saw in the election, if this soldier dies with this, if these 2 kill each other, still C1 has got more number of soldiers, right? Actually, here we have 1 less soldier. Now it is in majority. So initially it is in majority, right? Now if one soldier of C1 kills or dies with one of the soldier of all these countries combined, still C1 is in majority. The idea is, if you are removing one occurrence of the majority element with one occurrence of any other element, the majority element still remains the majority element. Can we use this idea to solve this problem optimally? Let's now bring back our example again, and let's try to do a dry run on the example. So we have all these numbers. Now, if I remove one occurrence of the majority element with one occurrence of any other element, let's see what remains the result. Okay, so if I'm removing 4 with 2, 4 is still the majority element of this remaining array, right? If I remove 3 with 4, again 4 is the majority element, right? If I remove 3 with 4, again 4 is the majority element, and finally we are only left with 4. Okay, cool. Now the question is that you don't know initially which one of these is the majority element, right? if you don't know which one out of these is the majority element, how are you going to cancel the occurrences of all the other elements with the majority element? The question is, do you need to know the majority element? If I slightly change the initial observation, so initial observation was that if we are removing one occurrence of a majority element with one occurrence of a non-majority element, the majority element remains the same. But if I change this observation to, if I remove two distinct elements at a time, if I remove two distinct elements at a time, the majority element remains the same. Will this also be correct? If instead of always selecting one of the majority element, if I'm selecting any of the two elements, making sure that the two elements are distinct, that is also going to cause the same effect, right? Because if you are not selecting one of the majority element, then this will definitely be in majority because you are not removing it, correct? So you don't need to know the majority element initially, okay? What you need is what is the current element that you have, okay, and what is the count of other elements. So if we are here, if you are trying to find the majority element in this array, you don't need to sort, you don't need to get the counts of all the elements. What you can do is you can just maintain a variable and you can maintain the count. So initially, when you are at 3, you can say that 3 is your majority element, count is 1. When you get another occurrence of the same element, you can just increase the count. Now you get a different element. When you get a different element, you can say that since this element is not same as this majority element, you can remove these two occurrences from the array. So you are not counting it and you are changing this count to 1. So this means that you have removed one occurrence of 3 and you have removed one occurrence of 4. Then you go to 2. Again, you get an element which is not same as the current majority element. So you will cancel out both of them. So now you are removing this occurrence of 2. So you are not counting it and you are also reducing this count from here. Okay. Then you go to 4 and now you see that 4 is the new element. And the current count of majority element is 0. That means if count is 0, there is no element that you have here, right? So now you can change your majority element to 4 and the count now becomes 1. Okay. Then you again go to 4 and you see that this is same as the initial element. So you will now increase the count from 1 to 2. You go to 2, you find that this is a different element. You can remove the counts. So if you remove the counts, you are not counting 2 plus you are decrementing the count of current majority element. Then again, you see that here you have 4. So you will increment the count. Again, you get 4, you increment the count. The final element that you are getting with non-zero occurrences can be your majority element. Okay. Great. If this is clear, will this always be the majority element? Will the final element which we are getting, is it always going to be the majority element? No, not necessary. This is not necessary that this element is always going to be the majority element, because there can be cases where there is no majority element in the array, right? This one. So in that case, whatever answer you finally get, you will have to actually count the occurrences of that in the initial array. So here if you get 4 with a count which is greater than 0, you will again, you will run a loop over your initial array and you will count the occurrences of this prospect majority element. This can be the majority element, not sure, okay? This is a prospect. This is the only candidate for a majority element. So if you get something here with a non-zero count, you will just check here and count the occurrences. If they are greater than n by 2, then you can say that this is the majority element. Okay, I will just repeat the counting part again. Okay, how we are counting. So is everyone clear with the idea of this algo? The idea is that whenever you get two distinct elements, you remove them. Okay, if you are getting two distinct elements, you remove the occurrences of those two distinct elements. So if I'm getting 3, and then let's say if I'm getting 4, I will try to remove both of them. Okay. So what we are doing here is we are maintaining a current majority element and we are maintaining a count. Okay. So if you get 3, you increase the count. So you have, let's consider a different example. Okay, let's take an example given by Vijay Sai, which is 3, 3, 3, 4, 4, 2. Okay, so we'll be maintaining a majority element and we'll also be maintaining a count. Okay, you get 3, you say that 3 is the current majority element. I don't know what is going to be after 3, but 3 will be the majority element. Count of 3 currently is 1. Then you go to 3 again. This is same as the initial or the current majority element. So you increment the count to 2. Okay. Then you go to 3 again. You will increment the count to 3. Then you go to 4 and now you get a different number. What was the algo? What was the initial observation that we made? The observation was if you remove 2 distinct elements, the majority element remains the same. So if I get 2 distinct elements, I will cut them down. So I will not count the occurrence of 4. So I am ignoring 4 and simultaneously I am also reducing the count here. Okay. Then I get 4 again. I am again reducing the count. Then I am getting another different number. So I am reducing the count. Count becomes 0. If count becomes 0, that means there is no majority element. If let's say there was another 3 and okay, so in this case, basically you are not going to get a non-zero count, but it might be possible that you can get a non-zero count even when you don't have a majority element, right? So you can have something like 1, 2, 3, 4, and then let's say 5, 5. Okay. In this case, if you run the same algo, you will get a non-zero count at the end, but there is no majority element in this array. So after you get a non-zero count, you will have to check in this whole array. You will have to count the number of occurrences of your prospect candidate. Okay. Okay. Rahul is asking, will it work for n by 3 problem? Yes. Okay. So in this case, the question was that majority element should be occurring more than n by 2 times. Now there is a variation of the same question which was asked in Google, where the problem says that your majority element is an element that occurs more than n by 3 times. Okay, now using the same concept, you have to solve this problem. Okay, yes, Ayush, this will work. Okay, if you want, you can also try to see it mathematically. Okay, you can just take an array of size n. Let's quickly see how if it is going to work mathematically or not, right? So the initial size of the array, size initial is equal to n, right? If you are removing 2 elements, then the size will be n minus 2. Now, if there is a majority element, then what should be the minimum count of that majority element in this initial array? That has to occur more than n by 2 times, right? These many times. If you have removed 2 elements, from this array, at least one of them can be the, or at most one of them can be the majority element, because you are removing 2 distinct elements, right? So the count of new majority element in this array is going to be n minus 2 by 2 plus 1, right? Is it making sense, guys? So the initial size of your array was n. After removing 2 elements, the size becomes n minus 2. Initial count of the majority element was greater than n by 2. So the minimum count would have been n by 2 plus 1. Now the count is size by 2 plus 1, right? And if you have removed 2 elements, only one of them can be the majority element, right? So what would be the new count of this element? The new count of this element is going to be the initial count minus 1. This is going to be n by 2. Okay. And if you solve this, this is also going to be n by 2. So you can see that this is the count of majority element which should be there in this array of size n by n minus 2. And this is the count of the initial majority element. So you can say that the initial element still remains the majority element. Now you can do the exact same exercise for n by 3 also, and you can check whether the same algo is going to work or not. Okay. What is the time complexity of this whole algo? So we are running a single loop, right? We are running a single loop and we are just maintaining the current majority element and the count. Okay. So the single loop is going to count you order n time complexity. What about the space? We are using only two variables, right? We are not using any array. We are not using any hash map. We are using only two variables. So the space is going to be constant. So will you be able to write the code for this? Could you go through an example of n by 3? Example of n by 3 is there in the test that you have received yesterday, right? You can just go through that problem and examples are listed there. You just have to check using this exercise that will the same approach work or not. If you are able to do that, then you can solve that problem as well. Okay, let's solve the next problem. Now the next problem is also a very, very interesting problem. Yes, the algo that we have discussed, this is the Moore's voting algorithm. Okay, so let's discuss the next problem. In the next problem, you are given a matrix. Okay, this matrix is sorted row-wise. All the rows of the matrix are sorted and all the columns are also sorted. Okay, what is a matrix? Matrix is nothing but a two-dimensional array. Okay, so all the rows are sorted in ascending order and all the columns are also sorted in ascending order. So here we have a matrix which is sorted all. So you can just quickly observe all the rows are sorted in ascending order and all the columns are also sorted in ascending order. Okay, you are given a target and you have to search the target in this matrix. Okay, so for example, if your target is 37, you have to identify whether the target is present in this matrix. If it is present, then what are the coordinates? Okay, so if the target is 37, 37 is present and it is present here, right? So you will be returning the coordinates of 37 in this matrix. Okay, is the problem clear? Okay, for those for whom the problem is not clear, I will quickly repeat it again. You are given a matrix where each row is sorted in ascending order and each column is also sorted in ascending order. Okay, then you are given a target and you have to find and return the coordinates of the target in this matrix. The dimensions of matrix is n cross m. Okay, what is the brute force here? Can everyone solve this problem using a brute force algorithm? We simply have to start from here. Okay, then traverse all the rows, each and every element, check if that is equal to the given target or not. Right? If you do this, what is going to be the time complexity? If you are traversing each and every element, how many elements are there? This is going to be order n into n. Right? There will be one loop which will run from 0 to n. Then there will be another loop inside that which will run from 0 to n. Right? Okay. Now, some of you are saying that you can solve this problem using binary search. Now, for all those who don't know how binary search works, you can just skip this part. We will be covering binary search in details in the upcoming classes. For all those who know how binary search is going to work, can you guys quickly think of an approach which uses binary search? See, all the rows are sorted. Okay. If all the rows are sorted and you have to search an element in sorted rows, can you use the fact that the rows are sorted? Yes. So in each and every row, you can apply binary search, right? What is the time complexity of doing binary search on an array of size n? If you are running binary search on an array of size n, the time complexity is log n, right? And if you are doing binary search in all the rows, how many rows are there? So in this case, we have n rows and the size of each and every row is m, right? So in our case, if we apply binary search on every row, if you apply binary search on each and every row, what will be the time complexity? There are n rows and there are m columns. So there are m elements in each row, right? So this is going to be the time complexity. Okay, cool. Can we do better? Okay, if we want to do it, if we want to do better, let us try to make some quick observations. Okay, if this is the matrix, let's draw a matrix here. Where can we find the smallest element of this matrix? Can you guys quickly tell me the coordinates of the smallest element present in this matrix? The smallest element of this matrix is going to be at 0, 0, right? This is the smallest because all the rows are sorted, all the columns are sorted. So this is the smallest of all. Where can I find the largest element of this matrix? The largest element of this matrix is correct. It's going to be at the cell n-1, n-1. This last cell, right? This is going to be the largest of all. Now, if the target element is smaller than 0, 0, or if the target element is larger than this element, can I directly say that that element is not going to lie inside this matrix? If your target is less than 0, 0, or your target is greater than the last element that you have, which is present at n-1, n-1, can we say that this target is not present in the matrix? Yes. What if this is inside the range? What if the target is inside the range? So if we are starting from this point, if the target is greater than 10 and it is less than or equal to 71, and I'm starting my search from this point, can the target be present in this row? If it is greater than 10, can the target be in the first row? Yes, because all the elements of this row are greater than 10, right? So target can be 30, it can be 40. Target can also be 17 or 15, right? So it can also be present in this column as well. So if the target is greater than 10, it can be present anywhere in the matrix, right? If we are starting the search from here, we are unable to make any conclusive decision, because all the elements here and all the elements here are following the exact same property, which is that they are greater than 10. So this is not allowing us to discard any of the search space, correct? Let us start the search from this block. Now, if the target is smaller than this, can I say that the target has equal chances of being present in this row, in this column, as well as in the last row? Because all the numbers in this column are smaller than 71, because the column is sorted in ascending order, right? All the elements of this row are also smaller than 71. So again, we don't have any decision that we can take, right? We cannot discard any part of the search space. All the values are still relevant. Okay. Let's try to search from this point. Now, can you guys figure out a pattern? If I'm standing at this point, if I'm standing at 50, what can I say about all the elements present in the first row and all the elements present in the last column? If this row is sorted in ascending order, can I say that all the elements of this row are going to be less than 50? Similarly, all the elements of this column will definitely be greater than 50. Is it going to help us make any decision? So if the target is less than 50, can I say that target will never be present in the first column? If the target is less than 50, the column is sorted in an ascending order, right? If the target is less than 50, all the elements in this column are definitely going to be greater than 50. So the target will never be present in this column. Now I am able to make a decision to discard some part of the search space. The search space has become smaller, right? All these values are now irrelevant. Okay. So if the target is less than 50, I can directly move to this cell and I can start comparing from this cell. Now, if the target is greater than 40, can I say that that target will never be present in the remaining part of this row? If the target is greater than 40, I know that all these elements are less than 40 because the row is sorted in ascending order, right? So now these elements become irrelevant for us. So I can discard this complete row. Okay, and now I can start my search from this cell which has 45. Again, I can check whether the target is smaller than 45 or greater than 45. So at every step, I am able to make a decision of either discarding one row or discarding a column. So let's say that if the target that we have to find is 26. Okay, if 26 is the target that we have to find, at this step, I know that 26 is smaller than 45, and since this column is sorted in ascending order, all the elements below 45 are useless, right? 26 can never be present in this part because 26 is smaller than 45. So I will move my pointer to 35, right? Now, when I'm at 35, I know that again 26 is smaller than 35. So all the elements of this column also are useless for us. Okay. So we move to 25. If currently I'm standing at 25, I can see that 26 is bigger than 25. If 26 is bigger than 25, all the elements present here are useless for us, right? So we move down. Now, when we move down, we figure out that this element is nothing but the target. So we have found the target. So in every step, we are either able to discard a complete row or we are able to discard a complete column. So you will be running a loop. You will be starting from the topmost corner, right? You will be starting your code. You will be starting your search from this top right corner. And you can say that if this element is equal to the target, then you can directly return true, or if you are asked to return the coordinates, you can do that. Now, if this element at the top right corner here is smaller than the target, then what can we say? We can say that all these elements are if this element is smaller than the target, then these are useful, but these elements are useless, because these all elements will also be smaller than the target, right? So what can we do in this case? We can just switch to the next row. So we'll be doing I++, okay? Else if this is greater than the target, then what can we say? If this element is greater than the target, then all these elements will also be greater than the target. So we can switch the search space, or we can switch the column to the previous column, right? So we can move to the previous column. So that will be J minus minus. Okay. And there will be a while here. Can you guys tell me what should be the condition which should come here when we have to stop all these things, when we have to stop the search? If we find the target, then we are returning. So that will obviously break this while loop. But what should be the condition? What should be the boundary cases for this search? We're starting the initial I value from where we are starting is 0, right? This is the first row from where we are starting. The initial column value is the last column, which is m minus 1. So these are the initials from where we are starting. Now, what should be the restriction, or what should be the boundary where we can go? This I. So now you can also pay attention to how we are changing these variables, right? So I is always getting incremented, j is always getting decremented. I is currently at the smallest possible value, which is 0. J is currently at the largest possible value, right? So if you are incrementing I, you have to make sure that you are not going out of this matrix from here, right? So I should always be less than n. Okay. And if you are decrementing j, you have to make sure that j does not become less than 0, right? So j should always be greater than or equal to 0. So this is your boundary case till which you have to run this loop. And if you find the target, it's good, return true. If this current element is less than the target, all the elements of the first row will also be less than the target. So ignore them, move to the next row. If this element is greater than the target, then all the elements of this column will also be greater than the target. So ignore them, move to the previous column. Okay. And we search the element. What is the time complexity? Some of you are saying log of m into n. Is it log? What is the time complexity? So to get to the time complexity, focus on what is the maximum number of steps that you are going to take. Right? What is the maximum number of values that I and j can take? I is starting from 0, it can go till n. J is starting from m minus 1, it can go till m. So what is the total number of combinations of these values that can be there? In every in other terms, you can also think in this way, that in every step, either you are ignoring one row or you are ignoring one column. There are total n rows, there are total m columns. If in the worst case, if the target that you are finding is present here, you will be ignoring all the rows above this and you will be ignoring all the columns after this, right? So the time complexity is going to be n plus m. What if matrix is not sorted? If the matrix is not sorted, you cannot apply this logic, right? Why not maximum of n and m? That is because you can do both of the things, right? If you are moving from this corner to this corner, you will have to take all the n steps in order to move from here to here, and you will also have to take all the m steps in order to move from here to here. This is the worst case, that you go down as much as possible and you also go left as much as possible. Okay, so that is n plus m of every row. Okay, Vijay, you can just try to see some of the example. Just try to dry run your approach on this matrix itself. You will find that chances of finding your element in every row will be there. So if, let's say, I am talking about, if I have to find 30 is smaller than all these numbers, right? So 30 can be present in any of the rows. 30 is greater than the first number of all the elements in the first column. 30 is less than all the numbers in the last column. So 30 has got a chance of being present in each and every row. So you will have to apply binary search in every row. And if you are applying binary search on each and every row, then that will be n log m. Pseudocode, we have written the pseudocode, right? This is the pseudocode. Oh, this is the actual code, not the pseudocode. This is how you are going to initialize your I and j, I from 0, j from m minus 1. Okay. And I hope you have learned something in today's class. Please do solve the problems and please do subscribe to the channel so that you don't miss any new class update. Okay.